是藻类啊，这种都是卡本。单碳可能接下来这5圈可能是要土壤都搞不定了，还要搞蓝碳。台大主要是供蓝碳。它应该是准时10点开始。
Okay, so it's time to start our team introduction. And hello, my name is Michio Sanjo, the professor in the laboratory of the advanced hydrohazard measurement analysis. And at first, I introduce the student or associate professor supporting this event. Okay, じゃあちょっとね。マキオさんとゴさんもぜひ来て、ちょっと前に。まずですね、he is Dr. 松本先生 is associate professor, assistant professor in other laboratory in DPRI.
Okay.
Yeah, and his professional field is study of the vegetation flow in rivers, vegetated flow. Yeah. 特に particularly he studies investigate the relationship of the vegetation and local sedimentation around the vegetation plant. それから、he is Uriさん。he is a doctor student of my laboratory and doctor grade 1, first grade. And he is studying about sediment transport in the sediment bypass tunnel in dam, artificial dam. And he will explain his study in the later part in this event. Okay,
thank you.
Now today's Usa can speak the Chinese, of course. So, I will use the Japanese, but he translate from Japanese to Chinese. Okay.
Okay.
Thank you.
Thank you. One is he is Charles Mateo, the doctor second grade, and he's studying about the coastal engineering hydraulics. So, particularly now, he studies the experiment of the tsunami. And he will explain his research topic later. Okay. じゃあ始めます。すみません。ここで日本語にこのちょっと待って。ちょっとすみません。じゃあ皆さんおはようございます。
おはよう。
宇治川オープンラボラトリーにようこそ。
我们在宇治川实验室欢迎大家。
で、私の研究室の名前はアドバンストハイドロハザードメジャーメントアナリシスという名前で、主に河川と海の水利学に関する研究をしています。
我们实验室的名字正如上面所写的，是为尖端水理计测实验室。我们主要研究是河川和海洋的系统。
それで、ここに示すように海の研究と川の研究の両方を行っているのが特徴になります。
我们特长是海洋和河川的水理学研究。
で、宇治川オープンラボラトリーには3つの研究室がありますが、海のことを扱っている研究室は私のところだけになります。
我们这边有3个实验室，然后我们特长是做海洋的。
それで、川池先生のところは主に川の研究になります。特に川の流れだけでなく、川池先生は川があふれたあと分かりますか都市の中の、氾濫現象まで研究するのが川池研究室の特徴です。
川池主要是做河川的研究，主要是都市河水泛滥的研究。正如它的名字所写的那样，需要做河流研究。
それで、今日の午後、中谷研究室の発表もあると思います。
今天中国老師也会发表。
中谷先生は山の方の研究になりまして、特に土石流ですね、エブリスフローの研究をされております。
中国的研究主要是做山里面的，比方说那边土沙流石的方面的研究。
それで私のところは、川と海ですね。だからそのあたりをやっていきたいということです。はい。
所以是主要是河海海洋这方面。
それで、実はこういう水の水害の研究には2つありまして、1つは水文学ハイドロロジー、それからもう1つはハイドロリクスになります。
我们这边主要是水文和水理双结合的方向。
で、特に私たちはハイドロリクスの方、力学的な研究をメインに行っていて、特に実験手法を使っております。
我们主要侧重于水理方面，主要做力学方面。
で、実験をやるんですけれども、実はですね、2箇所で実験をしてまして、1つはここの宇治川オープンラボラトリー、それからもう1つはまた別のキャンパスなんですけど、京都大学の桂キャンパスというところで実験をしています。2箇所で実験をしています。
除了在宇治川做实验之外呢，还在京都大学贵校区做实验。
で、海の実験設備はどちらかというとこの宇治川オープンラボラトリーにたくさんありますので、これ後でこの津波の水槽をご紹介します。
今天主要介绍海洋这个方面的研究。
川の方は申し訳ないですけれども、別のところにありますので、今日はちょっと詳しくは説明はできないんですけれども、植生の流れとか、あとは土砂の流れ、それから関係するこのタービュレンスですね、こういう乱流の研究を、桂キャンパスで主に行っています。
今天河川方面使用，因为我们河川方面的实验主要是在贵校区做的，所以不太能详细的介绍。像直升、土沙流石、川流之外呢，今天就暂时不详细介紹了。
はい。それとあとですね、ここにある写真は白浜観測所の写真でして、和歌山県ってここから南にあるんですけれども、白浜というところに海の観測所があります。で、そこで波の高さとか風の強さを観測しています。
右边这张图是在大阪靠南方面的白滨研究所，主要是做风波方面的研究，在量海波浪高度、水深等等。
で実験はどうしてもスケールが小さいので、実際の大きなスケールの現象と比較するために、ここの観測データを使うこともあります。
因为实验我们所做的规模其实并不是很大，所以在这边建立的实验室能观测到更大的方面，更大规模的获得更大规模的实验数据。
はい。で、これは私たちが使っている、水の、自然水域の、模式図にモデル図になります。
这是直升方面的一个模型，主要是由那个松本老师所做的实验。
自然水域には水の流れだけでなくていろいろな要素があります。
除了水的乱流之外呢，还有其他的因素所导致的，所以我们各个因素都会做那个实验研究。
例えばまず一番大事なまずこの底ですよね。ベッドの方からいきますと当然砂がですね流れて溜まったり掘られたりっていうこういう、土砂輸送の現象があります。
第一重要的当然是河床上方的土砂堆积、土砂流失等等。
それから、草ですね、プラント、こういうものがあると流れにとって大きな抵抗となります。
还因为这些直升的关系呢，所以这些土砂就会堆积起来，停留在这方面。
それで、もう一つですね、大事なことは、こういう抵抗物があると、そこで大きな渦が発生します。大きな乱流が発生します。
因为这些直升的这些抗体的存在，所以会产生乱流，这些涡流等等。
我々はこの乱流の、特性をですね、解明しておりまして、この乱流がですね、この土砂の、堆積の仕方に大きな、影響を及ぼすことを、研究しています。
所以呢，主要做这方面的研究，这些乱流等等，通过 PRV 来测量它的流速、涡流大小等等。
それからですね、これはあまり、世界的にもまだ研究が進んでないんですけれども、この風の影響も河川に、大きな、影響を与えることが分かってきています。
其实这方面的研究在世界上做的人并不是太多，所以呢，我们是主要，所以这是我们的独创性。而关于风方面呢，我们现在正在研究中。
風が吹くと、波が立ったり、あるいは、それによって、風によってですね、水面側に大きな乱れですね、タービュレンスが発生することが分かっています。
我们研究发现呢，风会导致水面波动非常大，然后这些正在认识当，这些实验结果呢，我们正在认识当中。
その結果、空気と、この水の中の、CO2 のガスとか、あと熱、ヒートですね、ヒートの交換が促進されることが予想されます。
我们正在预测当中，风对二氧化碳热量交换在对水面波形影响的研究中。
このようにいろいろとこういう環境に関する研究を、しているわけです。
这就是我们所做的实验。
で一方で、防災研究所では水災害の研究も重要視しています。
京都大学防灾研究所呢，主要是做水灾害这方面的研究。
例えばドリフトと流木の話も今すごく重要になっています。
比方说现在大坝河川当中流木所造成的灾害是有多大，这方面我们正在研究当中。
でそれではですね、一部しかご紹介できませんが、いくつか今やっている研究を簡単に説明します。
我们不能讲完我们当所有的研究，所以呢，我们会挑一些重点来讲。
実はまず雨が非常にたくさん降ると、山の方で、土砂災害が起こります。地盤が崩れる、山が崩れます。
因为天气灾害，所以导致水流灾害如图所示。
そうすると山にある木が川の中に、入ってきます。
就像图上所示，因为这些灾害，然后河道已经发生了变化。
で我々はこれを、流木ドリフトというふうに呼んでいます。
我们称之为流木drift wood。
日本だけでなく世界でもこの川の中で発生する流木による被害っていうのはたくさん報告されています。
其实这方面的灾害呢，在世界上也有很多的报道。
一番の問題は、この木が、川の中にたくさん溜まると水の流れを止めてしまいます。
因为这些巨大的流木所导致的河流会阻塞河道，使水流无法向下流域流动。
そうするとそこからまた外に水が溢れてしまうという災害が起こります。
所以就会使河川的水向外流出。
それを防ぐために、流木を、人工的に捕捉するキャッチメントテクノロジーって書いてます。捕捉する方法を考えています。
所以我们就会研究如何使这些流木捕捉这些流木，使这些流木不对河川造成影响。
これは一例一つのエグザンプルなんですけれども、流木が流れてくると流れてくる流木をここのなんていうかなデッドウォーターゾーンでキャッチするという仕組みになっています。
图所示是一个我们正在去做实验，是河流中的流木捕捉到将这些流木 catch 到这些左边这个湖泊池中。
で、川は上から下にまっすぐ流れていますが、ここに水生庫ブロインと言われる構造物をつけると水の流れの向きが変わります。
图所示呢，水流方向是从上往下的，所以我们在右边介绍这些构造物使水流方向改变，然后通过水流方向的变化捕捉这些流木。
特にこの水性によってブロインによって流れがですね、このデッドウォーターゾーンの方に向くので流木がこのデッドウォーターゾーンに入りやすくなります。
就这样，因为这些更较这些构造物呢，所以会使这些流木进入到这个纵里这个区域里面变得非常简单。
こういう研究であったり、あとはあまり時間がないんであれですけれども、あとはこれは、沈木と呼ばれる実験になります。沈木の実験になります。
刚刚我们介绍了流木的研究，现在我们讲沉木的研究。流木是指水面流动的实验，而这边的沉木是指沉降在河床上方的研究。
先ほどの、流木は水に浮くんですけれども、流木は一定時間水を吸うと重くなって、川の底に沈みます。
流木因为吸收了水分，使它密度变大了，然后因为慢慢密度增加之后呢，这些流木就从上方沉降到河床上下方。
それを我々はこの沈木サブマージドウッドと呼んでいます。
我们称之为 submerged wood。
で、通常の、通常の状態で沈木は川の底に少し埋まった状態であるんですけれども、これが、洪水の時に動くのか動かないのかを予想するのが大切です。
沉木因为慢慢密度之后呢，会被沉降在河床上方，然后因为 并被土沙所掩埋。但是在河水中呢，因为冲刷的关系，这些沉木到底是会被河水冲刷掉，还是依旧保持在原先的地方呢？这是一个研究课題。
それを調べるための実験を、行っています。
我们正在做这方面的研究。
で、あとはこれはですね、その動き出した沈木がどのように、下流に動いていくかを示す、図です。
关于这些沉木到底是被冲刷之后呢，如果移动的话是如何移动的呢？到底是向前滚动，还是跳跃性移动？是向河川两边移动，还是只沿着河流方向移动？到底是如何移动呢？正在这方面研究。
これは川を上から見た図で、流れは左から右に流れているというふうに思ってください。
这两组数据是从在实验水路的正上方拍摄到的数据，水流方向是从左向右的。左边的图是是沉木红色小长方形那样，然后是向两边移动的。而右边的图的红色小长方形，如图上所示，是沿着河流方向移动的。
すごくこの研究のキーポイントは、流木の最初の姿勢がポイントになります。
key point 那个重点呢是根据初始位置，它初始的角度所导致的移动方向、移动轨迹的变化，这就是被研究的重点。
例えばこの左の図に注目してください。
请看左边的图。
でこの場合は、沈木が最初流れに対して平行に、存在している場合になります。
左边的图，沉木一开始的那个角度是和河川是平行的。
でこの状態で流量が、少しずつ大きくなっていっていきまして、ある限界の流量を超えますと、沈木は動き始めます。
然后我们将流量从零开始慢慢增大，一直增到它移动为止。
ただ、まっすぐ下流に行くのではなく、斜めにこういう斜めにですね、川の岸の方に向かって動いていきます。
然后它是斜着向两侧移动的。
でどちらに行くかというのは、これは確率の問題であって、これは実験の結果ですが、大体2分の1の確率で右、左にこう動いていくというのが分かります。
然后呢，它到底是斜角是多少呢？这是我们研究课题，并且通过实验数据所得，它不管是往左边移动还是向右边移动，它其实是5分的。
で特にですね、川の岸まで、動いていくとそこで止まりますので、また川岸で、たくさんの沈木がこう溜まる結果になってきます。
然后我们通过大量的实验数据来测得它向两边移动的前进移动的距离。
なので、この場合はあまり長い距離を動くということはありません。
并且我们得到数据之后，向两边移动到停止之后呢，它就不再往前移动了。
一方で、この右の今度はケースになりますが、これは流れに対して直角にこう静止している場合です。
右边的图初始角度呢，是和那个水流方向成垂直角度。
この場合は比較的、直線的に下流側に流れていって長い距離をですね、流下していくということが分かります。
然后我们从实验获得了，知道了，沉木会向沿着水流方向移动到很远的距离，就这样离家出走了。
以上のことより流木とか沈木の計算というかその予測ですね、動きの予測というのはこの最初のこの姿勢が非常に重要になります。
然后我们就知道了，初始角度呢是一个非常重要的参数。
これは、球形の土砂粒子と全く 違う性質になりまして、すごく難しい問題です。
然后这和球状物体的移动方式是完全不一样的。
まだ研究が、進んでいる途中の段階ですので、今後またいろいろと研究したいと思っています。
另外呢，我们还会做其他方面的这方面的研究。
それでちょっとお願いします。これはちょっと後で。この図はその土砂のセディメントバイパストネルの話ですけど、これは後でモさんが説明します。
这方面是关于土沙流出排出的方面的研究呢，之後會向大家介紹。
これは後でまた、説明したいと思います。ありがとう。はい。で、これはですね、ベジテーションフローですね、植生流れの模式図になります。
就是指示的模型。
で、我々はですね、これまで、大体20年ぐらい、この植生の研究を続けております。
关于指示的研究呢，其实我们已经实施了20年左右。
で、こういうふうに、草があると、大きな渦がですね、発生します。
因为直接指针呢，所以会导致涡流的存在。
で、その植生のこの例えば配置パターンですね、植生のどのように植生があるかによって、土砂のたまり方とか渦の発生の仕方が変わってきます。
指针的密度等等、高度等等，会有4个方面的模式。
はい、こういう研究をしてまして、例えばこれは実際の水路の写真ですけれども、アクリルの板を切って、この植物のモデルをたくさん作っています。
左边这张图是我们现在做的实验水路，然后这些模型是用树脂做成的。
で、この写真は硬い植生で動きがないですけれども、流れに対して曲がる植生も作っています。
这些模型因为非常的硬呢，所以其实在这模型中水流是很难移动的，但是在上方呢会形成一些涡流。
今日先ほどご挨拶いただいた松本先生がこの植生の研究のエキスパートでして、この植生の揺れによって植生が揺れるか揺れないかでも非常に乱流の特性が変わることを発見しています。
然后由松本老师获得的实验数据呢，当这些模型到底是否会被水流冲刷造成形变，然后对水流的方向会有造成很大的影响。关于这点，我们从实验数据中获得的。
それで、ここまで、いろいろあるんですけれども、どうしようかな、いろいろあるんですけど、ちょっと最後に津波のちょっと研究の紹介を簡単にします。
最後呢，我们会讲一些关于金波方面这些研究。
皆さんは日本で能登半島の地震というのはご存知でしょうか？
大家知道去年的那个能登地震大家所知道。
能登半島、地震があって津波が来たんですけれども、これは津波が、川を遡上する様子を捉えた映像です。
这是我们在新泻上月时所拍到的海浪上河岸冲刷的图片，不是图片，那个视频。
でですね、これは新潟県の上越というところでなんですけれども、津波が能登半島の時の地震による津波が新潟までやってきました。新潟県は少し能登から離れてるんですけども、日本海岸にある町です。
新泻县上月市呢是在日本的北部，然后靠近日本海那边。
ここにですね、防波堤シーボールがあるんですけれども、こういうものをつけてても川の中にまで入ってきます。ちょっともう一回じゃあ、それで、それからですね、これも新しい試みなんですけれども、この矢印っていうのは流れの速さを表しています。
左边正上方呢是我们所建造的那个海岸堤坝，但是这些因为地震的关系，这些海水依然冲刷到了海拔之后，然后这些史料呢慢慢增大，是指流速慢慢增大。视频从开头再重新放一遍。
防波堤を津波が一部乗り越えている様子も分かります。
然后我们就知道了这些海浪是如何向自动轨迹。
はい。でこれが津波の先端になります。
这就是海浪的最前端的图像。
で、この映像は、日本の国土交通省がつけているカメラの映像です。
这是由日本国土局所拍摄到的视频。
で、これをですね、画像解析してこの流速を求めています。
然后通过这些获得的视频呢，我们通过测量计测获得了流速。
それでですね、こういう水面の、パターンですね、こういう、泡とか波とかのパターンの動きから流速を求める方法でして、バブル。
然后通过这些速度获得水面的，通过这些水速呢获得流速波，对不对？
でこういう方法を我々は PIV というふうに呼んでまして、かなり今いろいろなところで使われている手法です。
然后我们这个测流速的方法称之为 PIV，全称是粒子图像识别测速法。
次のでこれも同じ津波なのですけれども、これはですね、その先ほどの、場所よりもさらに少し上流側の映像になります。
然后这一样也是海浪推进的图像，然后但主要是这方面的图像是主要是靠近海浪最前方的图像。
ここですね、堤防がありますが、津波が堤防を乗り越えて住宅地の方に入っていく様子が分かります。
然后虽然我们建设了这些堤坝，但是海浪还是刷到了堤坝，冲进了居民的家里。
で、もう一回ちょっと最初から言いますが、最初ここ分かると思いますけれども、非常に激しい水の勢いがですね、勢いの激しい水が、堤防を乗り越えていく、そういう瞬間を捉えています。
左上角的图片所显示，海浪冲上了非常高的高度，大约是房子的2-3层这么高，非常的可怕。
で、私はこの時に、この災害が起こった後に現地の調査に行きました。
我们去年呢在实地进行了研究。
幸いに大きな怪我をした人とか亡くなった人はいませんでしたが、
还好没有造成太大的人员受伤。
あれですね、ただ水がですね、住宅の中に入っていたり、一部の建物が壊れたりという被害はありました。
然後造成了一些建築物、房屋的損傷。
ですので、こういうふうに津波が来るということも水防災の研究者としては考えないといけないことだと思います。
当然了，这方面的研究是每一个做水工防灾，一定是有关系的研究。
普通河川の、研究者とか河川の技術者というのは洪水の方の対策を中心に行います。
当然，对于河川研究者、河川工作者来说呢，水面防灾是第一重要的课题。
しかし津波の想定というのはあまりなくてですね、そのあたりが今後の課題だというふうに考えています。
但是现在呢，对于这些波浪、这些海波、金波的研究，做的人还不是很多，所以现在我们开始重点聚焦于这个。
それで、この後ですね、マテオさん、チャールズ・マテオ君から、津波の研究を紹介してもらいますが、まさにこういう話のことを彼は今実験で行う。実験で
接下来就来介绍金波方面的研究。
じゃあいいですか。まず質問とか聞きましょう。
有什么问題？
なんかあれば、はい。じゃあまずね、質問聞くわ。僕だからちょっとそう何か質問とかあれば。
大家有没有什么 any problem questions？English or Chinese？
Chinese
就是刚刚这个影片呢，这个流速的测量是在摄影机里面直接做，还是在后面带回来那个 lab 里面做的？然后夜间的话怎么处理？
この予測の計測方法は直接で映画からの計測で直接データをもらえるとか、またはこの PIV を使ってこの動画を分析してデータを書くとか、このベロシティは一体どうやって計測？
まず
もう一点はまた量の場合は光線は不足ので、一体どうやってこの
計測するかっていう。まずですね、まず一つ、日本には、こういうライブカメラというのがたくさんありまして、この動画を入手することは比較的簡単です。まずそこをちょっとお伝えしてみます。
做这方面，在日本做水工方面的实验室其实有很多，然后通过它这些视频带回去做，然后通过 PIV 的方式来测量流速。
ただし、流速を出すためには、事前に測量をしないといけない。基準点の座標を知る必要があります。
但是呢，测量这些流速，我们需要先建立坐标，然后慢慢的一步一步。
なぜなら、斜めから見ているので、画像が歪んでいるからです。
不管是正，如果图像如果是斜着或者正的话，流速测量的流速是不一样的。
で、そのために何をするかというと、目印になる場所のをまず探します。
我们先测量，先建立法向量。
例えばこの、動画だったらちょっと分かりにくいんですけど、この橋のブリッジですね。ブリッジの場所位置とか、あとはですね、ちょっと分かりにくいんですけれども、こういったところに何らかの建物とかがあれば、その建物をいくつかピックアップします。
通过多个参照物，像对右边的桥梁、中间的房屋和最左边的房屋，多个参照物，然后建立这些参照物来建立法向量。
でいくつかの基準点の座標が分かると、座標の変換というのを行いまして、例えばある画像の任意の位置のこの1ピクセルが、何メートルとか何センチになるかというのを計算します。
通过这些参照物的实际距离来获得每个像素点的距离大概是多少。
ただ、すごく今回難しい点が一つありましてこういう陸の方は基準になるものはたくさんあるんですけれども、この場合ほとんどがこう水で覆われているので、この水のところっていうのはなかなかこう基準になるものがないので、そこは基準点の数がですね、どうしても不足してしまう。
这次研究实验难点呢，主要在于这个河岸过于宽广，所以其实在河流中心呢是没有参照物可以参考的，所以在外方向到底是多少是比较难以测的。实际上每个像素点是多少去
？Y 值这样，这样。它的那个每一个蓝色的点，是不是就会变成在 database 里面是会有留存的记录的资料吗？还是说，而且它的一个影像里面最多可以存多少个点？有没有限制？应该是与像素有关。
像素有关，一般是在16×16这样子，16或者32×32。
但是它的点，它有办法记录。有，
会記錄在 Excel
OK。
そして他は最高に PIB を使って精度にデータを戻す。
そうです。なので、基準点をたくさん確保するっていうところがデータの精度の向上、解析精度の向上に関係してきます。基準点の数。
然後通过这些基准点，通过建立多个基准点，就是会使实验数据非常的精準。
これはまだ多分日本でも初めての試みでして、こういう流速ベクトルを出すというのは、そのライブカメラの画像を使って流速ベクトルを出すというのは日本でも多分最初の試みだと思ってまして。
这是我们非常自豪的点，就是这个方面的研究呢，在日本应该是首当其冲的，是目前为止是第一。
今後広まっていけばいいな。
然后非常希望在之后呢，进行将这测流流速方法将展开。
我们只有做过一个点，没有办法做到这么多，我没有做过类似这样。
一个点是指，
就是只能测一个目标，比方说一个弯弯，然后知道它的流速，但不知道这么多。
我々の研究は今までは1ポイントしかないの流速と減速をできるんですが、この前面の 2D の範囲、その広いの範囲の流速を減速方法はできないのちょうどです。
そうですね。普通は先生の通り野外のフィールドっていうのは1点しか測れないっていうのが問題なんですけれども、ただこれはこの方法の欠点を一つ言うならば、水の表面しか測れないですね。だから水面の下の様子がちょっとわからないのと、特に底の様子がわからないです。底の流れの様子が。それが今後の課題ですね。
然后我们今后呢，现在其实只能测量水面的流速，关于这些水面下方河底的流速到底是多少呢？将会是我们今后的问题。
特にですね、僕らがさらに知りたいところは、津波が来た時の砂の動きですね。土砂の動きを予測しとか評価したいんですけれども、水中のこの流れの様子がわからないというのが今の問題ですね。
现在呢，我非常想知道，就是这河里的流速是多少，并且重点关于河里这些土沙上行移动的流速是多少呢？是非常想知道，将作为今後的課題。
なので、もしそういう土砂の動きとかを考えるのであれば、一点計測でもいいので、ADV とかそういうポイントデバイスですね、点計測のデバイスの方が現状まだ優れていると思っています。
一点流速呢，其实是用 ADV 来测量。
だからそういう形ですね。
最 last question。
OK OK。
就是之前那个木头的实验，就是角度的那个部分啊，我们学校的一个叶老师啊，他有做了大概快10年的研究，他们是在做七地的那个，那但是木头的那个宽度跟你的曲槽的宽度这样子有没有一个比例？就是有没有什么宽长比？因为边壁也会影响到它的那个结果，水流会影響到它沖刷的結果。
人木に地形については、
人木、
はい、
あ、はいはい。人木ね。はい。
あ、次
これね。はい。
人木の、サイズとかの色の幅とかの比率は一体何なんですか？
まず、この水路の幅は、20センチです。非常に小さい水路です。これ40センチ。これ40センチです。40センチ。
水路的宽是40厘米。
40。
这种图所是0.4厘米。
これは実は彼が計測したものだよね。で、沈木の長さ6センチ。
然后沉木的实验模型是5厘米。
で、直径が1センチですね。直径が1センチ。
然后是用圆棒做的实验，它的直径呢是1厘米。
で、アクリルの模型を使っているので、比重が1より少し大きいぐらい。
然后模型的素材呢是树脂，然后密度大概是比1稍微高一点，刚好能只能降到5厘米。
で、関連して大事なポイントとしましては、土壌の状態が、滑面なのか素面なのかによってもいろいろと変わってくると思います。
然后合体呢，除了铝板的光滑面之外呢，还实验了将玻璃珠填沙的移动床作为实验。
で、これはどうだったかな？滑面でしたっけ？1ミリのガラスビーズを引いたりですね、なので、これも難しい話なんですけれども、沈木の大きさと、その今、下にある可消材料の大きさの比というのも非常に大事なのかと思います。
那个沉木模型的大小和床实验水柱大小非常有直接的关系。比方说，河床的40厘米会导致它向左移动或向右移动的话，大概距离会有多少，会产生一定的限制。
この実験は、1ミリの、ガラスビーズを水路に引いています。
然后移动床实验呢，我们是将直径为1厘米的玻璃珠铺设在水床上方进行实验。
で、その上を直径が1センチの沈木が動いているという
然後呢，将
状況です。
这个密度直径为1厘米的沉木模型放在移动床的上方进行实验。
で、この場合はですね、ちょっとこれもまだ検討中なんですけれども、沈木が先に動くのか、その下の砂が先に動くのかっていうところも非常に大事な話です。
然后呢，它到底是如何移动的，这是最重要的问题。
で、今回は沈木の方が先に動く。だからそうです。流量を大きくしていっても多少のガラスビーズは動かずに先に沈木が動くというそういう実験になっていまして。
然后流速呢是指你将流量慢慢增大，一直到极限值为止，这个沉木开始移动了，水流就不再增大了，然后才到这个。
今後の課題です。よければ皆さんも研究いただければと思います。
当然，我们希望大家做这方面的研究。接下来就 Charles 来发表他的经波研究。
また何かあればメールでもいいんで。
当然还有什么问题的话，我们可以邮件联系。
じゃあ、あとですね。あとは英語で、イングリッシュでクイズ
So good morning to everyone. Shugokoto Nihongo dekimasen. I don't speak English.
日本語ができないから分からない。
Shugokoto Nihongo dekimasen.
He said that he cannot speak Japanese and Chinese. so he is trying to
English.
English.
But it's a very beautiful English.
Ego desu. Anyway, I am Charles Mateo from the Philippines. As I will be explaining or discussing it with you, one of our studies here at Kyoto University, titled Experimental Study on Tsunami Forces and Overtopping in Civil Structures Under Wet Bed Conditions. So here is the outline of the topic. As an introduction, tsunami bores, actually the one that is being presented by Professor Sanjo a while ago is not a tsunami bore, but it's only a tsunami. Because tsunami bore are highly energetic wave fronts. One example is the tsunami that has been destructed or devastated the Tohoku region. So it generates rapid changes in velocity, turbulence, and flow depth, as well as it causes significant sediment transport and coastal erosion. And these high-energy tsunami bores can also inundate coastal zones, causing widespread destruction to infra, also loss of lives, and severe economic impacts. As a mitigation process, we use seawalls, and these seawalls are widely implemented coastal protection structures. They are designed to block, reflect, or dissipate tsunami energy before it reaches inland areas. So the effectiveness of seawalls depends on structural design parameters, tsunami wave conditions, and also the specific site hydrodynamics. In this study, we have this, most actually studies use dry beds or ideal setups. So here we use wet bed as well as different geometric designs in testing the effectiveness of these seawalls. So there is a real world simulation of wet bed tsunami impact. So this is actually the actual setup or wave testing facility used for this study. So it is actually located here at the laboratory of this Ojigawa Open Laboratory. Here is the 3D schematic diagram or experimental setup for the simulation. We use dam break method. So there's a spring-loaded gate that releases water to generate a bore-like wave. So the wave travels down the flume toward the seawall model placed on 5 centimeters from the gate. So actually, I don't have the point, but that's the seawall and also the building model behind it. And this is actually the actual picture of the spring-loaded gate. Also, the schematic representation of the experimental setup. So panel A, before the gate is released, water is held in a reservoir section at an initial water depth or reservoir depth. Okay, and then after that, there is a quick release, spring-loaded. It's not manual, but there is a release block. So the gate is released upward and the water is released. So it generates a tsunami bore-like wave. As well as downstream part is the 5 centimeter platform, as well as the seawall model and the building model behind it. So here are the experimental results of tsunami bore impact or interaction with different seawall setups. So this summarizes the interaction with 4 seawall types. So we actually tested 4 seawall designs: the slope, the curve, the stepped, and the box under initial or varying water depth conditions from 13, 15, and then at 17 centimeters. So the other next column is the overtopping height as well as the measured force. So here is the illustration, digitized bore direction as well as the velocity speed. So this is the interaction with the different designs, showing the slope, the first one, curve type, the step type, and as well as the box type. So arrows black indicate the bore direction as it approaches the seawall, as well as the red arrows reflect also the velocity speed. In this figure, the overtopping height distribution for 4 seawall designs under the initial varying depth conditions. So the box type seawall recorded the highest median overtopping height with values approaching to 4.5 centimeters. And the curve type and step type seawall both exhibited the lower overtopping height, so curve type and the step type. And as well as the slope type, despite having an inclined surface, this is actually the common design. It's still allowed to a moderate volume of overtopping, especially at higher water depth, so the slope type. And here is also the hydrodynamic forces measured, exerted on the 4 different tested seawall types or models. The box type seawall recorded the highest median maximum bore force with values reaching to at most 0.7 newtons. This indicates that it tends to experience strong direct impacts due to its vertical and non-dissipative structure. The curve type shows slightly lower force levels than the box type, but still with a wide range, suggesting that there is an inconsistent force behavior. The slope type exhibited a narrower force range, the slope type, and lower median value. And the step type seawall shows one of the lowest median forces and more balanced distribution, demonstrating its effectiveness in breaking down bore energy through turbulence. Also, here is the relationship between the overtopping height, the x-axis, overtopping height and hydrodynamic force for 4 seawall types. So there is actually a clear positive relation or correlation that is observed. As overtopping height increases, the impact force also rises regardless of the seawall geometry. So the box type seawall consistently recorded the higher forces for similar overtopping levels. And the step type at green triangle shows the lower force levels. The curve type seawall, the orange square, performs moderately, reducing force relative to the box type, but not as effective as the step type. Lastly, for the slope type seawall, the blue diamond follows a more linear trend, but its relatively high overtopping values suggests lower resistance to bore flow. Also, here is the time history of tsunami bore impact forces on the 4 seawall types. So in figure 8A, that's the 13 centimeters, the B is the 50, and figure C is the 17 centimeters. So we observe relatively low force magnitude across all seawalls at panel A, indicating a concentration of force. And we can also focus on 8C, the box type seawall, again exhibited the highest peak force in terms of the impact force, while the slope type shows the lowest. The step type consistently limits force magnitudes, demonstrating its effectiveness in reducing impact loads at higher energy levels. So in short, the step type has the best design mode. Here is the snapshots of tsunami bore impact. So we can clearly see here that at slope type, bore rides smoothly up the slope. So slope type. The curve type, the curve geometric configuration deflects the bore seaward, generating turbulence and splashback. But of course, there is some reduction occurs, but overtopping remains significant. As well as the step type, surface breaks the bore into turbulent fragments, leading to strong energy dissipation, but lower force and reduced overtopping. Lastly, for the box type, so you can clearly see there in the bore action, vertical wall causes an abrupt vertical surge, concentrating energy and resulting in high impact forces on the building structure behind it. So as a conclusion, the box type, highest overtopping and force, poor energy dissipation due to rigid face, slope type, high overtopping, energy flow downstream, limited turbulence, low energy reduction. The curve type reflects some bore energy, overtopping still occurs from crest pressure. Lastly, for the step type, best performance overall, lowest overtopping in impact force, it dissipates energy through stepped turbulence. So, seawall geometry directly affects overtopping height and the force exerted on coastal structures. So, incorporating this energy dissipating feature is really crucial, especially under wet bed conditions, which amplify or increases the energy, the velocity of the tsunami bore, and of course its impact force. So as a recommendation, we can also explore varied wave types and bore generation methods. We can also examine scale effects to improve real-world applicability, as well as we can also test the designs in diverse coastal environments for broader validation. So thank you for your attention.
Are there any comments and questions from audience?
No more questions.
No.
Many years ago, our school has the wave tank, and we have done similar flume tests and finding which kind of a seawall is better. But the picture you show us the bore force. Yeah, no, this the next page. Next. Yeah, this one. So, in consideration, two things. What matters? The impact force of the peak is the most important, or the last time is important, which is much important for the wall impact force.
Actually, it's the first
thing.
First impact. That is actually the.
But the tsunami is pushing.
Yeah,
it's always pushing us for a long period, not for 1 second. So maybe will it break on the second wave, third wave, or fourth wave? Maybe the first wave, maybe it breaks a little, but the second wave, third wave, it pushes downward.
So that's why actually we have the dissipating feature, the geometrical figure,
Yeah,
and also it contributes.
because you can see from this one here. You can see the sorry. This one. Thank you. So you can see the curve of the different kind of curve types. That type is descending, but I think it's the curve, the slope type is still lasting very long. This one.
And that's actually the box type.
Oh, the box type.
Yeah,
So the box type is extending, but this is energy dissipating.
Yeah.
But how is the bore force impact? Which because the wall is very high, so is one point measured or many points measured?
We only have the overtopping as well as there is a wave gauge fixed on the building structure behind it. So the force that is being measured is continuous. That's why we have the time history.
So it's the sea on the only one side is measured, the seawall.
Not on the gauge is not fixed on the seawall.
Oh,
It's the building model behind.
oh, the building. Okay.
The building, the total, he measures the total force against the building. So he could not consider the distribution of the force.
No.
Yes, total force.
Yeah, because the result here is 0.7 around, but this is small. This is only 0.4.
This one is 15 centimeters.
Yeah.
17.
17 is.
centimeters.
So it's making the wave jump high, and the impact force is bigger. And during the 2011 tsunami, the video show that many waves hit very high and push.
That causes also the.
Yeah. So some of the scholars from other universities, they are trying to find a curved wall that make the wave go back.
Yes.
Otherwise, if it's overtopping, it's like a slide. It pushes everything away. Then the impact force will be much bigger, maybe 2 times, 3 times bigger.
Just like the impact.
So the measurement, where is your sensor measured?
It's actually fixed on the building model behind.
Explain the press officer, house building.
Yeah. This one, there's a building model behind it. So
Oh, behind. Oh, okay.
this is this is the seawall. This is the bore action, and then on the building.
So it's like a impact force,
Yeah.
not the vertical.
Not
It's
horizontal force.
horizontal.
It's actually measured after the overtopping.
Yeah. Okay, understand. Thank you.
Thank you so much.
Okay. Asa. Thank you very much. Okay, from now we are going to the laboratory room, and I introduce our web.
接下来我会介绍一个关于大坝方面的一项研究。这项研究课题呢，主要先介绍研究背景。关于大坝的，像需要一条排水路来引导它的排沙，将排沙土石向外排出。而这个排沙通道呢，我们称之为 sediment bypass tunnels。然后呢，这项 sediment bypass tunnel 主要运用在瑞士和日本还有德国3个国家。然后，并且呢，像大坝科学院的大人物斯密先生、角哲野老师呢，会在最近的九州方面建造一个新的大坝，而这项排沙管道通通呢也会设计在这项大坝，河边川大坝运用于这个大坝之中。但是呢，管道当中因为土石的流沙，所以中间一定会进行磨损。所以呢，本研究主要聚焦于这个磨损，特别是管道中间这些土沙流失会对河边进行芦笋。而应对这些磨损方法呢，还是将在河川的底部建造一些构造物，来使得一定量的土沙堆积在河底，形成一个保护层，并且使构造物的上方可 可以将这些土沙呢轻松的流出，这样既能形成保护层的同时，又使得土沙能快速的通过这些管道排出大坝。而右边图所示的是实验中所使用的一些概念图，所使用的水路宽度是20厘米，长度为4米，测量范围主要在第2米到3米中间。而形成的模型呢，我们现在使用所示的，除了三角形断面模型之外，还使用了4角形模型。这张表所展示的是实验的所有水理的条件。使用的模型图所示的，除了三角形和4角形，边长为1厘米，长度和水路宽度是一样为20厘米，然后设置间隔为3厘米、5厘米和10厘米，然后所使用的土沙模型为直径为1毫米的玻璃珠，密度为2.5，然后将土沙投入到河床中的比率为图所示，每15秒或者30秒或者1分钟投入70克的玻璃珠进行实验。而水理条件呢，我们用伏卢格数来表示，滴流有3个档次，然后一档是2.0、2.80和3.03和3.92。流速测量方法我们则用 PRV 来进行测量。如所示，在上方进行激光照射，然后在河床的侧面将高速摄影机将动画记录下来，然后通过电脑通过实验，然后通过软件将流速测量得出。而土沙覆盖率则是用的是 OpenCV 的 MATLAB 进行，不是 MATLAB， Python 进行实验。然后通过土沙的覆盖率，我们可以清楚的得出哪种效果是最好的。接下来我们进行将聚焦于流速的分布图。图所示呢，然后这些粗度建造物中间呢会形成马蹄形涡流，然后这些马蹄形涡流呢会影响这些土沙的会堆积，这就是所使得这些土沙为何会流进这些粗度中间而排不出去，使得形成一层保护层。如所示呢，底下的灰色部分呢就是形成了良好的保护层所示。然后我们比较三角形粗度设计更好的还是4角形粗度设计更好的。然后如所示呢，在三角形粗度设计下会形成水面高变化的波形水面，这也会使得堆积在这些建造物中间的粗度更容易排出去，也就是造成了不好的影响。但是呢，4角形粗度呢，只是水面会形相对平稳，水面是非常平坦的，这样就会使流进去堆积在粗度中间的流沙不易排出，会形成更好的保护层。然后我们进行了单一子流，验证了为何流沙会堆积在粗度中间这些建造物中间的实验，将单一的玻璃珠投入到水面之中呢，然后慢慢一步一步的进行观测它是如何移动的。如所示呢，它是会慢慢下降然后下沉，但是呢，进入到粗度中间的涡形流之后呢，它会倒退到这些进行水流方向反向的移动，使得它堆积在这些粗度中间，这是证明了为什么这项功法是有效的。然后当然我们会观测它是如何这些玻璃珠、这些土沙是如何堆积在形成过程。如所示呢，这些沉降物的土沙呢会一步一步的慢慢排行到这边，并且可以看出，这些土沙呢最高高度、最高深度是为1厘米，就相当于等于它的粗度最高高度，意味着一旦堆积之后呢，多余的土沙会在粗度上方排出，而不会进行堵塞，也就是功法形成保护层的同时呢，也会使得多余的土沙尽快的排出这些管道之外。然后我们进行另外一项观测，当多余的土沙不会再流入之后，它会如何形成呢？ 当多余的土沙没有再投入到河床之后呢，它会慢慢下降，然后到一定的值，它就再不会变，它堆积量就不会变化，并且堆积形状也不会变化。这意味着呢，在清水状态下，干净的水流波动下呢，这些管道依然可以形成它的作用，并且这些保护层不会因为水流冲刷还会离开这些粗土中间，这些正道中间，使保护层依然安定的保护这些河床水面。最后呢，展示的是通过弗洛德树和粗土中间概率来形成它最好效果，这是它的概念图。左边的概念图呢，解释了为何这项工法是有效的，并且为什么它会使得土沙堆积在河床的底部形成保护层，并且使得多余的土沙排出。而右边的通过弗洛德树和间隔区间呢，我们可以找到最佳的设计方案。最后就是以上介绍的内容。
有没有问题？我问一下，就是因为一般我们认为那个排沙的那个道应该是要赶快把沙子排出去，但你的保护的那个厚度的部分其实是怕那个磨损嘛，对不对？
对。
怕磨损。那它的管道的部分，他们会不会定时的去做清理？意思是说，它清掉，是不是就会变成一个空间，又要等下一次再来那个？还是说你的目标是说，让它变成一个有点永久的 layer？
永久的 layers。
永久 layer。
因为我管的时间因为非常长嘛，除了入口和出口之外呢，中间部分是很难进行维护的。
对。
所以尽量呢，并且大坝设计者应该都会希望大坝的可持续性非常的高，比方说。讲这个大人物所说的1000年大坝，那么我们当然是希望这些磨损会越低越好，所以呢，这些保护层最好是尽量全覆盖的。
全覆盖。所以你的希望就是你的整个面都是一个 bar 这样子，
对，
或者是一个三角形的 bar 这样，一个是三角形嘛，一个是 rectangle 的那种 bar 这样子，所以是一整条。所以它因为光这样看是有点像是 one dimension， 就是它的鱼的情形，但它不会因为因为大部分的管子应该都是 circle 的吧，圆的。
不是，它底面应该是平面的。
哦，底面是平面的。
它是类似
open channel 这样子。
这个样子。
哦。OK。的确这个，所以你的间距的话是。
间距的话是根据实际比例进行比的。
对，所以是大概是多少是最好？目前。
是1比50左右，一般会设计在实际大概会设计在2.5米左右。实验设计的最佳距离是5厘米左右，然后粗度高度的话是1厘米，所以比值的话就是5厘米1比5。
所以它到时候那个设置，就是因为你刚刚有到，我刚前一页有看到它的那个70%，在应该最后面的那个地方有一个看起来7%，对，这个右下角右边这个看起来也还，就是说到60%多最少，对不对？
当然设计间隔越短的话，它堆积效果一定是最好的。但是考虑到成本的话，我们会尽量找到一个平衡的值。所以
70几这样子。
70几左右，当然80%以上，我们当然是认为是最好的，70几也是可以接受范围。
算是经济分析了。谢谢。其他有没有什么问题 ？OK， 这样，谢谢。
没有的话，今天上午就到此。
好，谢谢。
bit about our laboratory and my study, mainly on the debris flow. So today, my lab's target is about the sediment transport system and mountainous regions to rivers and coastal area. And we have two large missions. One is the sediment disaster prevention, like debris flows and woody debris from the mountainous area, and also some sediment and flood damage in the downstream area. And also, another one topic is understanding the sediment dynamics in sediment transport systems. So we sometimes go to the debris flow field investigation, also have some hydraulic experiment for debris flow, and also sediment production monitoring, and sometimes sediment transportation monitoring, and also assessment of the climate change, impacts of the sediment runoff, and doing some enhancement of the hazard maps. So today's PM schedule for our laboratory. Now we are thinking about having the seminar about approximately 2 hours. So we have 5 presenters, staff, me and Dr. Yamanoi, and we have 3 PhD students. So Mr. Iwai, Mr. Totsugi, and also Mr. Rai. He's a visiting student from Taiwan. So we all have a very short presentation. And after that, your side each, we will have some presentation. And then maybe we have 5 or 10 minutes short break. And then we move to the laboratory for doing the sediment, debris flows, sediment experiments. So this time thinking about 1 hour. We'll set up the channel for experiment, and we'll divide into 2 groups of the students and conduct the experiment. Here, I'm thinking of setting 3 different flows, 5, 10, and 18 degree. And in 18 degree, we can set some sub-grounds and add large boulders and woody debris and see the change. So this is the channel we are using after this seminar. It's a kind of rectangular straight channel with 7 centimeter width, 2 meter length, and variable slope. And also we're setting crosspiece for the roughness for the channel. So this channel is for explaining the debris flow and bed load in the mountainous area, and also considering the sub-grounds against debris flow. So, about the debris flow occurred in the town, these are some pictures of the debris flow. So you can see some large boulders. Large boulders like 1 or 2 meters, and some woody debris because it's come from the mountainous area. And sometimes we also have large boulders that also fine sediment. And because debris flow is mixed up with the water and the sediment and sometimes woody debris, and usually, woody debris and large boulders come into the front part of the debris flow. It can damage to the houses or cars, roads, and maybe to the people. So this is a photo of the debris flow and also woody debris. In 2013 in Japan, here there was a bridge here also. Usually, the water or sediment pass through the channel, but in this case, woody debris has come out with the debris flow. And in the frontal part, and then this bridge was blocked with woody debris like this. So the debris flow was expanded. The sediment and water and the woody debris you can see around everywhere. So that this woody debris can cause damage. This is also the picture of the woody debris and Hiroshima and Yamaguchi. And sorry, this is Japanese, but last year, we also had some kind of debris flow. This is Shiba Prefecture, next to the Kyoto. There was a mountain Ibuki. There was debris flow coming out, and here we can see about it exists. Some houses demolished. So this is when we go to the field research. The upstream part, this kind of very 1 or 2 meter erosion has occurred. And also, this is in Ehime Prefecture. Well, this is behind the Matsuyama Castle. There was a landslide and then debris flow occurred. And in this disaster, unfortunately, 3 people was damaged. So every year we are having this kind of debris flow in Japan. So for the countermeasure against debris flow, we have stubble dams. Usually, we set this kind of cross-type stubble dam, made a kind of a concrete wall. And also these days, these kind of open time column is also installed. Because the debris flow from that part woody debris or large boulders will be accumulated. You can see usually here is open, but these large boulders and woody debris come into the frontal part and block. Then a fine sediment will be also catched. And this is another, not a thermal dam, but we call debris flow breaker. There's a screen, flattened screen will separate the water and the sediment. So because debris flow is a mixed up of water and sediment, to separate the sediment and the water, it will be, the movement will stop. So it can be, damage can be small. And usually after debris flow occurred, even this subclosed type or open type or debris flow breaker, we have to remove the sediment or remove the debris with the heavy machines. Well, this is the sediment transportation. Usually, the bed material rock, sediment transportation can be divided into the massive motion and the individual motion. So massive motion, it's the mixture of the water and sediment, and the movement of the particle sediment is done. And in individual motion, the sediment movement accompanies the water movement. And usually the large, steep slope, large particle, and high concentration is kind of debris flow. So sediment, the high concentration of sediment and water. And sediment sheet flow, maybe the kind of Chinese character is easier to understand. In the lower side, the high concentration of the sediment and water, and in the upper part, the water flow. And coming to the more mild slope, it is a bedroom. So only very small particle, it's low concentration. So this is a video of the debris flow, sediment sheet flow, and also the bed flow. So that's why I'm thinking about 3 degrees. So in today, 18 degrees is the debris flow. In 10 degrees, you can see the sediment sheet flow. And in 5 degrees, you can see the bed flow. See? So when the slope is different, the sediment transportation behavior becomes very completely different. So I would like you to see it is going to be like this change. And also for the debris flow, we can see how the thermal dams will work. So this is another topic in what we are doing these days. So this is not a usual open road, but we have another this kind of channel. And in this research, we are changing the bed with a rough bed and also smooth bed. Considering that like mountainous area and here maybe roads or channel. So see you can see the rough area and the smooth area, the behavior has changed. Now we are doing this kind of topics. And also sometimes we go to the field investigation. This is a debris flow occurred in 2018. Here, debris flow come out for this rainfall. And usually in this kind of area, there's a culvert. So usually in the daily rainfall runoff, water will come in through the culvert and then go underground channel. But usually when debris flow or this kind of sediment disaster occurs, this culvert is blocked with sediment or debris or something else. So the culvert cannot mark effect. So in that case, usually debris flow will flow down the road. In this case also here, this channel, this culvert didn't work, so this flow down in this way. So this area here, so it comes here and debris flow, sediment, and also water itself has moved down to this residential area and caused damage. And this is a kind of result of the debris flow simulation for the deposition and also for the maximum flow depth. And there's another introduction of the debris flow simulation in 2014. You can see from the disposal photo that many debris flow has coming out, and also it's spread in the residential area and caused high damage. So this is one photo. You can see some rocks, sediments, and some houses are destroyed. Well, this is a more detailed one. These were completely destroyed. Here, the blue color is the landslide erosion, and it able to orange is the deposition. This is another torrent. Here, debris flow has flowed down through the road, and maybe this kind of area, deposition has occurred much. I had made some debris simulation for this F2 area using the digital elevation model taken before the disaster. And in this case, we use the hyperconical system. This is the system based on debris simulation. Well, there's another one for canonical too. This one is open free software in Japanese and English, but the hypercanonical is a little updated, so we can use DEM and also using the GIS. If you are interested, more information, it is usually Japanese, but this is kind of shared software. But for the foreign user, and not for the non-commercial use, sometimes we give it without any fees. And in hypercanonical and canonical, it is based on the Takahashi model of the debris flow. We have the momentum equation and the mass conservation equation for the total debris flow, and also for the sediment. Because debris flow's volume will increase or decrease due to the erosion or deposition. So we have the total debris flows, mass conservation, and the sediment conservation. And also, so the erosion and deposition is very key for the debris flow behavior. There's an equation for the determining riverbed change. So the riverbed, due to the time scale, maybe it is coming lower, it is erosion, and coming higher will be the deposition. And this is one result of the debris flow in one abnormal flow depth and also seeing the deposition. So you can see 2 hours in a row, the debris flow is going down, and here is the large damage. And also, come here, you can see some large deposition happening. This one is another case. Well, this one, only deposition, but considering the house and not considering without the houses, you can see the behavior is a little changed. And in the middle of the disaster, it was close to this. So in the residential area, it is useful to considering this kind of houses. So applying this kind of neighborhood simulations, maybe if we can set a suitable scenario in land floor, scale, or other parameters, we can know the realistic neighborhood behavior. And also the influence area, so we can apply for the effective evacuation or maybe for the top-down construction. Okay, that's the end of my presentation.
Questions?
Maybe you can ask now or maybe during the experiment. You can also ask or have a discussion. So maybe, is it okay?
Okay.
We can meet today, have a noise instead.
Small present.
Thank you so much.
Small present.
Okay, so good afternoon. My name is Kazuki Yamano from DPRI Kyoto University, and today I'd like to talk about this topic. I cannot pronounce it here, but that topic is numerical calculation of the effects of sediment production on inundation during the Noto Peninsula earthquake and subsequent heavy rainfall. And I'm not sure you may know or not, but 2014, the beginning of this year, the heavy earthquake was happened in Noto Peninsula, and the magnitude was approximately 7.5 or 7.6. And as a result, this area, in this area, more than 500 people died due to the heavy earthquake. And this is some pictures of the earthquake damage, and many buildings are collapsed, and also the heavy fires in the city is also occurred, and many people died here. And not only this kind of damage, but also the landslide happened in the Noto Peninsula. And sorry that the figure is a little bit small, but the red colors indicates the landslide or debris from happened in these earthquakes. And you may see the blue area here. And blue area is tsunami inundation area. But today my topic is focused on the landslide. And after the earthquake, and September 20, from September 20 to 22nd, the heavy rainfall is also affected to this area. And this is some overview of the precipitation. And in totally, more than 400 millimeter precipitation was occurred in the northern Noto Peninsula area. The 400 millimeter is not quite large, I think, for Taiwan, but in Japan, especially the northern area, this value was something very large. Okay, so and due to this rainfall event, the landslide sediment was transported to the downstream. And also, not only the sediment, but also the wood debris were stuck in the at the bridges, or some additional landslide was happening beside the road, or in the. This is an example of the river dikes was collapsed due to the flows from rivers. Okay, so and today I'd like to focus on this area we call Machino River. Machino. This is the temporal change of the Machino River's state, and this is the state of before the landslide, before the earthquake, and after the earthquake, many landslides was appeared here. And after the rainfall, this is the picture after earthquake, and this is the picture after heavy rainfall. There's several landslide, additional landslide was appeared here, and also the zooming to this area, something like city area. This is the earthquake-induced landslide. And this is the heavy rainfall-induced landslide and the inundation area here. And from this aerial photograph, we can see the sediment was transported from this catchment and inundated around here. And this is the photograph taken by the drone after the heavy rainfall. You can see the sediment was accumulated in this river. We call this river Suzuya River, and the Suzuya River is fully covered by the sediment. And then the riverbed was aggregated, and finally the sediment was deposited on these agricultural area. And this is the opposite side of the state, the Suzuya River, and we can see the deposition area of the sediment and woody debris here. And government conducted the LP, the laser profile observation before and after the heavy rainfall, so we can use the differential data of the elevation, and we can see the deposition beside along the river bed, and also in the downstream area, something like this. And this is the background of these studies. During the Noto Peninsula earthquake on January 1st, the large amount of sediment was produced, and also then after the rain, during the heavy rainfall, additional slow failure occurs and sediment are transported to downstream. And the sediment outflow likely causes geomorphological change, which may have influenced the extent of flooding. I mean, the extent of this area, the flooding area may change by the sediment because the riverbed was aggregated here. So the challenge of this study is make the numerical simulation considering the sediment production due to considering the sediment produced by the earthquake and also the rainfall runoff. So this is the purpose of this simulation, to track the immobilization earthquake generated sediment using rainfall runoff and sediment transport simulation. And this is Japanese, right? And the numerical simulation was conducted by using these methods. I hope most of character was Chinese character, so you may feel something like not quite difficult. But what we do is integrated simulation of the rainfall runoff and also the transport of the bedrock, the suspended road. And to consider the sediment produced by the earthquake, we set the sediment caused by the earthquake, something like this. And then conduct the numerical simulation of the rainfall runoff and also the sediment transport, something like this. And these are the input of the simulation. This is the elevation and also the land use. And also I intended to input the sediment observed by the differential LiDAR observation. But unfortunately, the ground was deformed by the earthquake itself. So in here, in this area, the total topography was aggregated, something 3 meters. So here, most of all area was, the elevation was changed to the higher. So to modify the DEM data before the landslide, I used the INSA data obtained by these researchers, and I used these data to modify such deformation. So, and finally I got these data. You can see the landslide happened here. I mean, the blue area is eroded and the red area is deposited. And by inputting this sediment as a movable sediment, so maybe we can track the transport of the sediment during the rainfall event. This is something like comparison. And this is some example of the input of the material. And I went to the target area and get the direct samples, and our students conducted the CV and then get these results, and I used the value of this red line. Okay. And I run the numerical simulation in the server, and then get the temporal change of the water depth all over the catchment. Also, the deformation, I mean the deposition or erosion due to the sediment transport. And maybe you can see the temporary change of the topographic deformation during the rainfall event. Something like this. Okay. So, and finally, we can compare the results with the aerial photograph. And this is some example. And the blue area is the outlet of this river, and the heavily damaged by the sediment transport. And you may see the deposition area at the outlet of this catchment is reproduced without the large, how to say, and we was, how to say something, agreed with the observation. But unfortunately, we can, fortunately or unfortunately, nowadays we can use the differential LP data. This is a very precise observation data, and we can directly compare the simulated results with the observational data. And we can discuss the quantitatively discuss the results. And as maybe this circle is something shift left, but I like to focus on here, and we can see the deposition volume is slightly, not slightly, roughly overestimated comparing with the observation data. So now I'm still modifying the parameters, something like the grain size distribution, or the rainfall infiltration parameters, or the condition of the sediment. Adding the process of the additional sediment production during the rainfall. Yes, and this is the small conclusion. I conducted the two-dimensional rainfall rate sediment runoff simulation here to get the, actually I intended to show the sediment transport, to show the influence of the sediment transport to inundation, but still we need to make this simulation better by changing the parameters or adding the modifying the simulation code or something. So we're still trying to proceed this research. But today I'd like to share these preliminary results to you, and maybe because this event is quite large event happened in Japan and very major targets. So this is the small results here, and thank you very much.
Small. The last PPT, yeah, this one. During simulation, the bed surface N value is all the same from the upstream to downstream because you collect the sediment size to input into the simulation. So is it due to because the circle you find it in simulation, a lot of deposit is downstream, but in this one doesn't have. So maybe is it caused by the N value of the bed downstream?
Yeah, you mean the sediment grain distribution may differ.
Differs, yeah.
Yeah, but actually now I use only one grain size distribution to whole area. That's large measure problem, I think. And in the upstream area, the grain size might be very large, and the downstream area may be very small. And we can conduct the transport simulation considering the different grain size. But the point is the lack of data of the observation. I only have these data, but it's difficult to. I have similar data, but it's very difficult to set the grain size distribution location by location.
Yeah. Normally we ask the students to collect the upper side of sediment, but if you do simulations, we normally go to the upstream, and you see the scouring of the riverbed. We could not collect the riverbed sediment. We collect the side sediment, and normally we collect underneath 1 meter. Not the surface. So the surface we will negative, and we collect 1 meter below sediment. and then the result might be better because we want to find the because most of the landslide induce the debris flow, so maybe the deposit might income. But if it is a landslide dam and breakthrough, maybe this kind of sediment is good for watching the spread.
Yes.
So different nation is influence the result.
I agree that it's very important. Yeah, I wonder every time I went to go to this kind of area, every time I wonder which sample we should collect. And this time,
very hard to decide.
Yes. Yeah.
Okay.
Thank you. So much.
So, can I change the order because this PC has started Windows update.
大丈夫。
自分からでも大丈夫。
Little present.
Thank you so much. Oh.
T2.
Thank you so much.
村井さんのやりる順番で。お願いします。高山。
Hi, nice to meet you. I'm Kanda Kotsugi, first year of the doctoral program of Kyoto University. Today I talk about the study on sediment deposition characteristic of the road drilling onto roadways. Last year, I belonged to the Hiroshima University, so I picked up the research target area in the Hiroshima Prefecture, and as shown the two pictures, July 2018 and August 2021. The picture of the landslide disaster highways. My research topic is landslides, disaster of highways, and I want to identify the road and deposition characteristic of landslides on the and debris flow. Sometimes, like this picture, road blockage is caused traffic jams, and finally, these roads took a long time to restore after the disaster. So I want to identify the characteristic. This is a background. In Japan, more than 10,000 mountain streams intersect our highways. But due to low improvement rate and maintenance rate, so we have to pick up the contaminated point. So indicated this picture, I roughly simply divided into the three types of the blockages. First one is a no inflow, and second one is a one lane block, and the third one is all lane blocks. And also the impact against the traffic sound is changed. And in my research, I use a hydraulic model experiment and a fluid experiment machine. The final goal is to investigate the sediment deposition characteristics on load. I showed the image of the fluid experiment machine. And after the result, I researched about 3 points: dispersion angle and sediment area and the amount of sand, and 3 topics. This is a picture of my experiment machine. The main characteristic is frame length is 15 meters. Relatively, the machine is larger compared to other machines. I introduced into experiment conditions. There are many parameters of the film experiment machine, so I have to pick out disaster. So I selected 2021 Hida Hiroshima town in Hiroshima Prefecture. I said, sorry in Japanese, but film slope or wide, slower length, so the amount of sand particle size, average particle size fluctuates. And I changed the condition, 2 conditions, embankment height from 0.7 meters to 3.7 meters. And also I changed the sediment concentration of the leaf flow from about 0.35 to about 0.50. This is the result of the low density like that. So I set a model experiment, model of the embankment of highway, like that. So middle density and high density. So I totally 36 cases. And after this, I conducted an SFM. SFM is a computer vision technique used to reconstruct 3D structure from 2D image taken by from the different viewpoints. I showed this picture. I took over 150 pictures, and I made a model for the landslide on road. I ran the movies of my 3D models. Like that, I can conduct it and I can publish a 3D model of landslide on road. And finally, I use this data of the amount of sand or something research. It's enabled to compare to numerical analysis of landslide. Like that, the particle size is, average particle size is about 1.8 millimeters, but the accuracy is a bit good for other methods such as LiDAR. So I selected SFM. Like that, I result compared to other results. So first method dispersion and good the amount of sand. Like that, I conducting I'm focusing on the highways and the roads. I conduct experiment and numerical analysis. Finally, I want to identify the characteristic of deposition of the leaf flow. Thank you for listening.
Questions?
No question.
Yes. The difference flow comes down because in my laboratory we did similar things, but it's the junction of the river. So 2 rivers. So you won't have lateral river scouring in this side. But I was thinking how much water when you release, when the deposit is formed, is there any more water being given? Because during typhoon and during heavy rainfall, it's continuous rainfall. So it will affect and also push, sometimes push farther. So do you only consider one-time deburst flow? So no more water. The backwater is you don't consider, right? Okay. Because normally it sometimes it goes it turns because of the water, and also you can see the grain size. Like the first one, it is a little bit turned to right side. So if the water is enough, it will push, it will turn. So the deposition and the length will affect too. We also consider this kind of thing, and also like Professor, you mentioned curvature on the curvature under the it will make the deburst flow jump. So sometimes the jump will let the big rocks spread. So it makes the length become very short, not very long. So different structures do affect the result. But the angle of the bed is fixed.
Yes, 18 degrees.
18.
Yes.
Thank you.
Can you use HDMI? Do you have both?
Oh, yes.
I will.
Hello everyone, I'm Lai Dongyang. I'm a PhD candidate in National Cheng University, and now I serve as the visiting student in the DPI. So today I'm really happy to see the Taiwanese professor and students come to the Kyoto. And it's also my pleasure to introduce myself and share some research results with you. So first of all, I talk about my research interests, which includes the river morphology evolution analysis. I focus on the mountain rivers, and the second part is the riverbank grain size analysis, and the third is the sediment-related disaster, which I focus on landslide and debris flow. So today, I will focus on I will share the results of the river morphology analysis, and mostly a little about the river grain size analysis. So the photo shown on the right-hand side is my main study area. The name is Laise River Watershed, located in Pingdong County. So this watershed experienced a heavy rainfall in 2009, which the scale is about 20-year return periods brought by Typhoon Rock. So you can see the figure on the left-hand side. A large amount of the landslide happened, and the landslide and the sediment transfer into the river make the river morphology change significantly. So the end of my study is to record the response and recovery of the watershed landslide and the river morphology after the extreme rainfall, so as to provide the references for future sediment management. So first of all, I talk about the results of the watershed landslide evolution. The figures shown on the left-hand side records the evolution of the landslide rates and the annual maximum 24 hours rainfall. As you can see, from 2010 to 2023, the rainfall intensity is less than the Typhoon Rock happened in 2009. So the landslide rate gradually decreased in this watershed. And we can use a landslide recovery curve to describe the evolution of the landslide rate after the extreme rainfall. The equation is shown here. So the YT is the landslide rate after the event, and the YP is the landslide rate before the event. Delta Y is the landslide rate caused by the event. So we can use the actual landslide rate data to regrade the coefficient alpha. So once we get the alpha, we can compare the different speed of the recovery of the landslide rates in different watersheds. So the right-hand side some results in different watersheds. So these curves may have the potential to estimate the landslide rate after the extreme rainfall. So back to my starting ridge. So in the river morphology part, I focus on the riverbed elevation, riverbed slope, channel width, and rating index. And here is the results of the elevation change and the slope change. The left finger shows the change of the channel height. I set the reference points before the Typhoon Rock to set the elevation as equal and compare the elevation after the typhoon to its value. So I can calculate the deposition height in different years. So we can see in the beginning, after large amount of sediment transfer in, the riverbed elevation increased significantly. In different ridge, it increased from the 8 meter to 13.4 meters. And then with the reduction of the sediment input from the hill slope, the elevation of the channel gradually decreased. However, we can also find that the different trend happen in the upstream river and the downstream river. So in the beginning, upstream river just insists. However, the downstream river, the elevation increased because of the sediment input from the upstream ridge. And we can find the similar trend in the change in the river bed slope, which may be induced by the river self-adjustment. And here we also find there are two events happen in 2021 and 2024 to make the elevation increase again. And here is the result of the channel width and the gradient index. And the change of the channel width is follow the degradation or degradation in the channel. It is also because of the river self-adjustment. So the channel width expanded in the beginning and then gradually declined. And after two typhoons in 2021 and 2024, and it expanded again. So here I make a quick summary. So the figure shown on the left-hand side is the recovery degree of riverbed elevation in 2024. So the recovery degree is, I calculate the elevation difference after the typhoon divided by the aggradation because of the typhoon. So the darker color, the color shows the higher recovery degree. We can observe that the upstream ridge recover more quickly than the downstream ridge, and which may result from the better transport capacity. And the figure shown on the right-hand side is the recovery degree of the channel elevation, riverbed slope, channel width, and the gradient index. And we can observe that the recovery degree of the riverbed slopes is the highest. And however, we also the results of the channel evaluation shows that there is still a large amount of sediment deposition in the river. So these two results potentially demonstrate the difficulty of river self-recovery in the following year. And here a little about the riverbed grain site analysis. I have tried two methods to analyze the riverbed grain site. One is the photosynthesis method, another is roughness analysis method. These two methods can both to use for the larger scale or the frequency analysis of the grain sites. And here talk about the results of the roughness analysis. So the roughness analysis is based on the topographic data. And I compare the roughness to the grain sites, and here can build the relationship between the grain size and roughness. So in the future, we may have the chance to use the roughness data to calculate, to estimate the grain size data. And luckily, our lab has some high resolution topographic data. And last week, we went to the field and do some sampling. And this is just some recall. So maybe I have the chance to do the analysis of the grain size in Japan's river. And here is the end of my my presentation. And welcome everyone to Kyoto. And if you have any question about me, please feel free to contact me. So thank you for your attention.
Any question? Chinese, okay. Any? I ask. Okay. His boss is also my teacher too. Yes. Okay. English. Last one. Okay. So when you mean recovery degree, so what is the difference? What is how do you calculate with before? What is the before difference? Before the typhoon or before the last event? What is the result?
Okay. I'll take the elevation as example. I calculate the different rates of the elevation between the 2024 to 2010, which is the elevation after the typhoon as the after one, and divided by the aggregation caused by the typhoon, which is the elevation differences from the 2010 to 29.
Yeah,
yeah.
But one question is that, like the recovery degree, 50 to 70 degree percentage there, because I did some construction there. So will construction affect the result of your research? Because I did excavating project, dredging. So at this part I did 3 times, and this I did 11 times. So every time we have small afternoon shower, and then the gradients come up. So it's up and down, up and down. So your recovery rate should, recovery degree, maybe you have to find near events. Then you can be, the recovery result might be better. Or otherwise, in this site here, the deepest deposit I remember is 27 meters. So we are still on the deposition site. So I think sometimes it is because on this branch, the upper region is a very big watershed.
Oh.
Yeah, so it might bring many sediments down also. So that might be.
Yes, the Rachel is very famous, familiar with this ridge. Yes, and lots of the dredging work have been done in this area, just mentioned from the Professor Lee. And since we have recorded the topographic data from 2021 to 2024, and for me, we sometimes, mostly we conduct the survey after the rainfall season. So because for this river, there is still a large amount of the sediment in the upstream part of the river. So after the rainfall season, the sediment will go transport to this part of the river. So mostly the dredging part will be full, just like mentioned from the Professor Lee. So the topographic data here, I will assume that it is not impacted by the dredging because still large amount of sediment will transport to fuel the dredging work. But yes, it may be some impact. But now I didn't count the effects of the dredging work in the long-term study.
Because the branch there is, right now it's scouring and scouring. So that is another problem. Scouring makes the deposition down to the left side. Yeah, it will affect too. And his professor told the Chief Bureau of Soil and Water Conservation Bureau, he says, if no construction involved in at least 25 years, you have to wait 25 years for recovery. 25 years. It's a long time. So the percentage, your investigation is very important. Otherwise, your boss will be very mad.
Yeah, thank you very much.
Hello, I'm Tomoya Iwai in this laboratory, and I will talk about sediment transport in the rivers. I will focus on debris flow associated with volcanic activity. So, this in here in Nagasaki Prefecture, there is a mountain volcano called Unzen again. Okay? And 1991 to 1997, this volcano erupted many times, and during this period, more than 800 debris flow occurred. And this is a pyroclastic flow, and I checked license, so maybe this term is correct in Chinese. And this flow is consists of high temperature gases and also this kind of solids. And debris flow is consists of water and sediment. And in this period, many debris flow occurred, as I mentioned, and now, even now, the houses damaged by debris flow is preserved in Nagasaki Prefecture, and actually this is a photo I took, so anyone can see the feel the debris flow. So why the debris flow occur after eruptions? Before eruption occur, rainfall will infiltrate into the slope, and rainwater slowly leaves the river channel. But after the eruption, the surface of the slope is covered by volcanic ashes, so rainwater do not infiltrate. Most of rainwater do not infiltrate into the slope, so surface flow occurs on the slope, and with the surface flow occur on the slope and fade intensely into the river channel. And sediment, the discharge will dramatically increase, so the sediment deposited on the channel becomes debris flow. And our field is, we have observatory in Gifu Prefecture, and we call Hodaka Sabo Kansokusho, so Hodaka Sedimentation Observatory. And in the top of the catchment, we have, there is Yakedake. This is also volcano. And Yakedake erupted in 1925. This is a picture at this eruption. And we made the numerical simulation by using seamless storm-induced multi-hazard information simulator. And so first, we divide the catchment into unit channel. This is a straight rectangular channel, and this is also rectangular slope, unit slope. And based on this topographic model, the calculation was made first for rainfall runoff on the slope, and after the water transportation was calculated based on transported equation. And this is a brief conditions for analysis. And I set the rainfall condition constant rainfall intensity, so 1 meter per hour, 2 meter per hour, and 100 millimeter per hour. And they continues for 60 hours. And I set two kinds of infiltration capacity, so 10 millimeter per hour assumes the condition after eruption, and this one assumes the condition before eruption. And the target catchment is shown here, and here is Mount Yakedake, a volcano, and this is a catchment we call Ashia Raidani, and I will focus on this channel first. And this is a example result. And, this axis means rainfall intensity. So, for example, here, 20 millimeter per hour of rainfall intensity was supplied, and it continues for 60 hours. And this blue line means the critical line of the debris flow occurrence. And this is a results for F equal 10 millimeter per hour, and this one is the results for F equal 100 millimeter per hour. So this is a critical line of the occurrence of debris flow, and this is also the critical line. And this 6.55 millimeter means that the cumulative rainfall was needed this value to occur the rain and the debris flow, and this is also means the minimum value for the occurrence of debris flow. So before eruption, 600 millimeter of rainfall was needed to occur the debris flow, but only 1% of rainfall was needed when the infiltration capacity decreased. So I can say that if the infiltration capacity decreases, the very small amount of rainfall can occur the debris flow. And this is another numerical simulation result, and I conducted in the whole catchment of the Ashia-Raikani, and this is a movie. So this shows the channel which occurs the debris flow. Red part means river that which debris flow occurs. And this kind of rainfall makes debris flow in some channels, but this kind of rainfall, so it doesn't continue for a long time, but in this time, 30 millimeter per hour rainfall occurs such a many debris flow. So this kind of long duration rainfall do not occur, do not make debris flow in every channel, but this kind of rainfall can easily occur, make that debris flow. So this is the, thank you for listening. 最後の写真This is Ashia-Raikani. So in winter we have many snow, and we try to record the moment of sediment production. And this is Hokkaido. So this is also a kind of volcano, and this kind of volcano also make disaster, but also we can get benefit from this kind of volcano.
Small question. In your simulation, why you use 60 hour? It's a long time because these particles are very small. Erosion will affect a lot.
The
60 hours.
The main part of the simulation is maybe high intensity rainfall, whose duration is short, and also this kind of rainfall. So the rainfall intensity is not so much, but the duration is long. So this kind of rainfall is not unrealistic, but we we use numerical simulation, so we can also consider this kind of rainfall.
Yes.
So this is not so important part, but I just try to calculate.
How deep is the deposit of the volcano deposit? How deep it is? Because infiltration is influenced, so you have to maybe set up the movement thickness. Yeah. Otherwise, you will have infinity erosion.
In this calculation, I set the thickness of the sediment to 2 meters.
2 meters.
Yes. But I tried another cases, but I just briefly introduced some results.
Okay. So is everything eroded? 2 meters all eroded, or just some?
Actually, I consider 2 mechanisms, and blue line means erosion from surface.
Yeah. Surface. Okay.
This green line means erosion, not erosion, a kind of sliding. So in this area, so this side of the green line, sediment, all the sediment will slide. But this blue line means sediment in the surface only will run. And how much sediment will, I didn't consider how much sediment will run.
No.
I just consider debris flow will occur.
Because we did some simulation resulted in Kyushu Asu volcano, and it's the ash is very thick, and after rainfall, normally the rainfall does not go inside; it just wash away. So it is very hard to form high concentration of debris flow. So maybe the CD is around 0.4, maybe not bigger than 0.45. Yeah, so it becomes erosion, not debris flow in this kind of situation. And because your infiltration is 10 millimeter per hour, it's very low. So that means erosion is a major event, not if the infiltration rate is 100, then the whole mass will move quickly. But it depends on the slope, because you only mentioned 12 degree is your gap, not gap. So this is interesting. The simulation is interesting because you can find what part is eroding, what part is deposition. I think Mount Asu volcano is the downstream is have the same problem. And last time we visited there, and they were doing constructions using the ash and put into a dam structure. The fill inside, and they are because they are preventing it from scouring. So they use the sediments to control, set a saddle dams, series of saddle dams to control the erosion. Yeah. Very good result.
Thank you.
Wait, why only me?
Almost ready.
He's a little bit hurt his hand because yesterday went to push the door too hard. Because our PhD students and most of the masters, maybe right now in Taiwan, we are majoring in green energy, and we have to consider climate change. And last week, we are in the main campus, and Professor Fujihara and then us discuss some things that we are doing, like for irrigation systems, how are you going to make hydropower? Some of us are going to JPGU next week in Tokyo, Chiba. And Ray is in green energy, and so another kind of thing that Taiwan is right now facing, green energy and also carbon problems. So like the ones that you mentioned about sediment erosion. Sediment erosion also causes CO2 to release, so we have to control CO2. Then I think another problem in Taiwan is we have to do constructions, and before construction we have to consider the life of animals and do research about how the environment is involved. So these three topics, majorly these students are doing a lot of things. And the PhD students, some of them are in agriculture. I think this topic is much more interested in for you. He can speak Japanese, so if you want to speak Japanese, go ahead.
Okay, greetings. I'm Raihan Landepiastomo. I'm from Indonesia, and now I'm studying in the逢甲University in the PhD program for infrastructure planning and engineering. But I think after heard that, some of you might think that why is the different topic than your college. Basically, I'm continuing my research from master at逢甲University regarding the green energy. And now I am helping my professors to build the green energy power plants. So currently my concern is the green renewable multi-purpose anaerobic digestion reactor power plant. And I added a concern on natural water resource because in this power plant we need water. Okay, so the contents of the presentation will be as usual. Introduction, then problem and current situation, my research, and the future perspective of the research. So what is green energy bioplant? Any of you ever heard that? Oh, nice. There is one guy. So my laboratory's main topic is the anaerobic digestion reactor power plant, basically using the fermentation to produce biohydrogen and methane. But don't worry, this is not a greenhouse gas methane. You can burn this to produce, not to produce, you can use it as a cooking gas. It's like a propane gas. So the anaerobic digestion converts organic waste into biogas and fertilizer. As you can see in here, this is one of the facilities of our power plant in Manado, Indonesia. So this is built on the slaughterhouse. It's where the beef and porks are produced from the cows and pigs. So the waste we use is basically a feces and a waste from the slaughterhouse, excess meat, lards, and their foods and their faces, bones, and then other materials, of course, with the plants. So Manado slaughterhouse plant reduce waste pollution, produce renewable energy. They wanted to be independent from the grid. So why this was built, I will talk it later. This supports the sustainability and the circular economy of the local people. So it's already independent. This facility can power up the slaughterhouse without needing of any power grid from the main line. This is how the power plant works. So the waste water is where the waste is being tanked, contained, and then it will be processed into the power plant. It will produce the biogas, the 1.5 meter cube a day, to use as a bioelectricity. You can power up the slaughterhouse, no need for the main grid anymore. And the excess of the liquids and the solid one will become the biofertilizer. If you can filter the liquids also, it is a pure, clean water you can drink. And the case 2 is not only the big power plant, but based model on the power plant, we made a small size. This is the size of this one. So only 2 tanks of water is needed to produce this. This is actually mini scale power plant you can use. It's installed in the Manado City rural area where the infrastructure is not good. So the access will be bad. In Indonesia, we cannot use any gas from the pipes like in Japan or Taiwan. No, we still use a propane gas tank, small one. And to transport this propane gas tank, we need some trucks, of course. But because in the rural area of the Manado is still have bad infrastructure, yes, of course. So the local government provided this mini size of the anaerobic digestion reactor, so they can produce their own cooking gas from their food waste, garden waste, or any agricultural waste. It has merit of the simple designs, so we don't need some sophisticated process to make it. And the starter bacteria is from the slaughterhouse main power plant. That excessive bacteria will be moved here, rest for 2 weeks, and they're ready to produce the gas. And the substrate or the bacteria's food is from the locals. It's from the household food waste, their garden waste, agricultural waste. Anything is okay as long as you can make it like a congee. Mix it with water, put it inside, done, every day. And now problem and situation in Indonesia regarding the water resource and environmental hazard. Have you ever imagined how the Indonesians live in Indonesia country? Indonesia is a big country with a lot of islands. It has approximately 18,000 islands, including the big ones, small ones. But because of this, a lot of area is still intact from the electricity. You can call it desolate area or remote area. They don't have any access to the electricity or any power. So if you go to the internet on Google and search about the Indonesian electricity percentages, they will probably tell you 96% or 98%, but that's a lie, don't believe this. It's very lower than you might think. Because the main grid only has in the big island. It's very hard to see from here, but you can compare the up picture and the down picture. The down picture is the nighttime electricity. Well, you can say the fully electrified place. There is a lamp, there's a 24-hour electricity running, and you can see in the night. Then you can see, compared to the default ArcGIS map of a main grid line. So this part of Indonesia is still intact with electricity, not fully connected to the main grid line. This photo is taken from last year at the southmost area of Indonesia. It's called the East Nusa Tenggara. The specific place is Bunak and Helong. These people are still living in the ancient manners in Indonesia because they cannot afford to have electricity. The closest electricity they can get is the port town, where you have to buy the fossil fuel and buy generator. So it's very expensive, they don't need it. They still live in the ancient manner, no money, barter only. And from the ancient living method, just like hunting in the forest. And some of them are still trying to farming rice, but still their dependency is from the forest. And like these people who needs power and electricity in Indonesia, there is a lot of places like this in Indonesia. So the solution my laboratory present is a remote, for the remote area like this, is a small scale bioplant using the anaerobic digesting method, because the anaerobic digesting method doesn't need any electricity. Depend on design, they can also add the electricity system into this plant design and make it bigger and produce more electricity. It's possible. However, if a place like this, it's better to have the smaller one, which is the simpler design, and you can just put it at very cheap, affordable. So the next problem is the water resources. The anaerobic digestion, by its nature of the fermentation, we need water. For making sake, miso, shoyu, there are also fermentation process and they need clean water, right? However, the anaerobic digestion doesn't need that clean water. Even the how do I say it in Japanese? Fuyo kasui. The contaminated water from the rice field that there is a lot of fertilizer inside, the nitrogen, ammonium. You can use that as a water for the anaerobic digestion. However, the problem is the water resource underground. In Indonesia, we are rich of the resources. However, these resources also can be poisonous to us. For example, in Papua, there is a lot of mountain. Papua underneath is a plutonium and uranium, natural plutonium. And from the water that is reside underground and going outside, sometimes it's radioactive. Sometimes it has heavy metals inside, even though it seems very clear. It's very dangerous in Indonesia. So the problem is a water-related hazard. Each island has a different problem regarding this, and we don't have any standard protocol for this one, unfortunately. A little bit contamination is okay, but the contamination of water that contains the bacteria killer, also it's a problem. We cannot use that as a digestion. If we use that water, of course the bacteria will die. There's nothing inside the reactor. So my current research is anaerobic digestion bioplants. This is my research. It's a bit very complicated if you see the picture, but let me just explain you. Using the power of the bacteria and the sugar chain substrate, boom, hydrogen, N. So simply put, the bacteria is the main role in here, so we have to maintain the bacteria's life as long as possible. And each bacteria for the bacteria is called the methanogen, and this bacteria is different for each island, including Indonesia and Taiwan, two difference. Taiwan has also methanogen bacteria from the locals, and we are using that in our laboratory to produce and simulate the reactor in a small scale of 3.5 liter. But the Indonesia's bacteria is a bit different from the Taiwan. The Taiwan bacteria needs a comfortable environment to produce the hydrogen, and usually it's on the mountain side. So, however, in Indonesia, the bacteria doesn't need that comfortable environment. They are very tough, but the problem is the biohydrogen production. It's a bit low compared to Taiwan. However, you can put anywhere. That's the difference. So we have to research every places. However, 18,000 island is too much for us. Continually, this is my current data of the production of hydrogen. It's a rate, so it's a percentage. The substrate is sugar water. The bacteria likes to eat the sugar chain material, not fructose, lactose, anything sugar. However, it's the chain. So as long as it's the sugar chain, they can eat it, like rice, for example, or maybe the agricultural waste. That's also a sugar chain, cellulose, hemicellulose. And in the production of hydrogen, if they eat a lot, they will become acidic. So they need something to control the pH so they can stay live. And that's usually a nitrogen chain material, ammonium, and maybe the basic one, or like the sodium hydroxides. And usually in the reactor, we mix between the sugar substrate and the phases, that is the basic of ammonia, or maybe the fertilizer water that contains nitrogen, so it keeps the pH between the 5 to 6. In my laboratory, the working volume of the reactor is 3.5, and I'm currently on research of the upscaling this, so we can have a bigger power plant. The reactor is inter-emittent magnetic field. We use the magnetic field to induces the bacteria to produce more hydrogen. It has a paper on it. You can search it on the Science Direct or Elsevier. With the Na, sodium hydroxide, as a control, it's the cheap one we can get in the laboratory. But this sodium hydroxide as a control, you can use the phases or any nitrogen chain material, such as ammonia, is okay. So the future perspective for this research is my learning expectations. It's the natural water resource treatment, actually. We already have the tools in Indonesia, but we don't have the researcher. That's the funniest part. The natural water resource in Indonesia is different, and also the treatment will be different. In my hometown, it's called the Bogor. It's a mountain city. My house doesn't need any water infrastructure from the city because we have unlimited resources water from the underground, and fortunately my house is a safe one. So we can use it for the shower and drink it directly. However, not the city area of the Bogor is need for a water infrastructure because the water is too dirty. And another place, like I showed the Manado before, their dependency is in the river, not the water, the underground water. So the different place, different treatment and different traditions. It's a big work for Indonesian people. And the natural water resource management also differ. Some of places needed water resource management. Some of places they can manage their own water, and some places they need to connect from the another place. The water hazard at Indonesia is currently not open one. So treatment is only limited into each university, each department of university. For example, in my city, there is one national university that is an agricultural university, and their water treatment method is different from the other university because it's mostly focused on my city. And the water waste management from the power plant, this is also one of my topics. So after the use of the anaerobic digestion, the water is called the effluent is still mixed with the dead bacteria and some waste water and other things. And normally we use a filter, and the filtered material of the solid one will go back to the tank and the water will be released. But we still want to learn more about this, how we can do it more simple way, or maybe we can make it a one system, so it will be another water treatment system beside the current one. Okay, thank you very much. If any questions, you can ask me. It's okay. 日本語でもいいですよ。
I have a small question.
はい、どうぞ。
日本語の方がいいですか？
どうぞ、大丈夫です。
最初のプラントのやつ。
はい。これですね。
それです。どれぐらいの how much volume of the waste they use?
The volume of waste they use is 12,000 liters each day.
Each day?
Each day. But because we don't have that big tank, so we divide it into the 3 tanks of 5,500, and usually it fills about third of the tank. 3分の4くらい。
そこ、インドネシア。
はい。
And the next one?
Next one.
So how do you bring the material to the plant? I mean,
using the pipes directly.
Only the pipe?
Yes. So the pipes will transfer the waste from the slaughterhouse into the wastewater ponds, and they will pump it to the mixer in the reactor.
I see. And for the next, I mean, the orange colored one.
Okay, this one?
Yeah, this one. At the moment, they need to bring manually.
Yes, because this is no automatic, this is very manual one, simplest design we have. And you put the waste into here, and the gas will be flow from here. And when the gas is filled, the tank will be flow up because there is a gas inside. And the gas that is used for here, usually the 3 to 4 days of food waste will turn into 30 minutes of propane gas. Yeah, that's another topics from us because we have to increase the optimizations. So at least 1 day of the waste can produce good enough for 1 day of gas. The simpler the design is, the optimization is harder actually because we need to add something. And also we need to research about the bacteria because this place bacteria is already different from my home's bacteria or another place bacteria. And also we cannot bring the bacteria to Taiwan or any other country because of the treaty. If we do that, I will get caught in the airport.
So maybe the local people also use the waste for agriculture, right?
Yes. The inside of this reactor is filled with a lot of bacteria and also the effluent of the bacteria. So you need to periodically pump this out, the effluent, And the effluent of this one is usually become fertilizer. They are good fertilizers.
I see.
The problem in this simple design is actually human. So currently the operational one is that out of 10 is only 3. So the other seven who held this simple design reactor is too lazy to feed every day. So only 3 of them are very diligent to maintain the reactor and enjoy the free gas.
Thank you. Yeah.
Anyone?
Right.
Yes.
Did you insist? It says that it's 4-day waste food.
4 days of pure food waste. So if you add more like agricultural waste, garden waste, and you can produce more gases. However, as I said before, you need to make it like kanji. How it's nakadoro-doro mitai. Yeah, it's like a muddy one. So you have to cut it through. You have to mixer it, or maybe you have to make it like solutions, not in the hard one, but it's a liquid one. That's the problem, and only the diligent people are able to do this.
But you says 4 days. Do you actually have an exactly kilogram how much?
No, exactly no.
But what happens if this tank is full at the moment?
As you can say, in the back there is a pipe here. This is a level control pipe. So unless you reach here, it will not go too much. So there is a control of gas about there. Okay, any question? I saw the voice in the back. Yeah. Does it?
I'm curious. Is the efficiency of the facility be affected by the environment?
Excuse me, can you repeat again?
Does the efficiency of the facility be impacted by be changed by the environment, like a high temperature will change its efficiency?
Yes. Because as their nature, each bacteria has a different characteristic for each environment. And because we took from the environment and we incubate it, nurture it, and we can use it as a bacteria of methane and hydrogen producing bacteria. So each place bacteria and each environment will affect the reactor. Also the foods. This in Manado, we only use the agricultural, we don't use the agricultural waste because people are doesn't want to have a time for grinding the garden waste into some kanji and muddy taste substrate and put it in. They just use the food waste, but still it can produce enough gas for 30 minutes of cooking. And you said if the environment will affect the reactor or not, it will affect. In this picture, what kind of substrate you can see here? It's the leaves, the trees, right? So the types of leaves, trees, agricultural waste also having impact and effect on the bacteria. It's like American people and Japanese people. Japanese people eat healthy food, they are very slim, they're cute. In American people, they eat a lot of McDonald's. They get big and obese sometimes. It's already too different, right? Even though it's the same human. It's the same as bacteria. What kind of food they take, what kind of environment and places they're in, it's affecting them. Okay, any question? Yeah, sure.
Okay, thanks for your presentation. I want to see your experiment result.
Okay. It's still data, not result.
And I wonder that what kind of sugar you used in your experiment?
My sugar, it's a fructose, normal sugar. You can buy it on the supermarket.
Is that polymers or not polymers?
Yes?
I mean the molecular weight of your sugar is larger or not? Is that the polymers or not polymers?
Oh, you asked that. Oh. So I use the sugar from the supermarket, not the white one, the brown one, because the refined sugar is too chemical, and so we want to make it as natural as possible. So we use a brown sugar. That is the one that you can make on the traditional way also. And then we also add the nutrients for the bacteria here, in case the bacteria is weakened or needs some help to grow up. So the sugar you ask is the one that you can find in the supermarket. That is the brown sugar. The bacteria is more fat than me.
Sorry, I mean, your experiment, you use some simple sugar, but for the AD reactor and in some farming, we can put some, some sugars. We only use, for example, you said the food waste or agricultural waste. That might influence the biogas production rate.
Yes.
So, and another question is that what's the purity of your biogas? Is that will influence the burn ability?
The purity of the biogas is every day the biogas produced my reactor is not in here. It's around 10 liters of biogas, and the purity of hydrogen inside is around 30%. 30% is the best one I have right now. However, my colleagues have like 50%, 60%. I don't know how they make it. And the stable one is around 20 to 30% contents of the hydrogen. My reactor is a small one, and we make a removal of the methane. We don't want the methane. We want the hydrogen first, not the methane. Methane can also use a biogas to burn for the propane, like for the cooking, but it also a greenhouse gases, right? So we want focus mainly on the hydrogen. If they can produce hydrogen, it means that they can also produce methane. And you say you ask for the purity of the hydrogen or the methane on the reactor that is already set in the area, right? We actually don't know. We need research. However, we don't. First, we don't have the facility. The second one, we are not allowed to move outside the area. Well, of course, if we send the reactor in with the bacteria inside to Taiwan, I got caught, probably in prison right now. So I have to do the MOU research, the joint research with the other university. That's a difficult one, if you know. But yes, the purity is good enough for the burning, for the combustible gas, because the flame is blue, not orange. It means that high temperature combustions means the high purity of the gas inside.
Thank you.
You're welcome. Yeah.
I have a question in previous stage.
Yeah, sure.
Yes. I'm sorry, I'm not familiar for your research, but I know hydrogen is very dangerous gas.
Oh.
If the hydrogen mixed with other gases, it is easy to explosion. So
Okay.
I want to know how can you ensure the safety of your experiment?
Good question. No one asked that questions. Good and nice. Yes, hydrogen is a dangerous gas if it meets oxygen. So you all must know what the term of hydrogen bomb, right?
Yes.
It's explode very big with the small amount of hydrogen. And even if we use the hydrogen as a fuel, there is a risk of explosions because the combustion of the hydrogen is very dangerous and it's highly explosive. But if this one is combustions, if combustion means the oxidizations of the hydrogens, so if oxygen meet the hydrogen, it will become the explosion. However, if the oxygens already become the another material, it doesn't react with hydrogen. What is this another material? Is the CO2. So, yes, so the reactor produces the pure hydrogen, methane, CH4, and that's carbon dioxide. They don't produce oxygens. That's why we call anaerobic digestions. There is no air inside the reactor, only the bacteria. Nice question. Okay. Anyone? Usually after this profession we have questions.
No.
You already asked last week.
Okay.
Thank you very much.
Because but in Taiwan we are facing the problems I mentioned, and agriculture waste in Taiwan is very enormous, and also after disaster, also many agriculture waste. So food production is always more than need. So some of our farmers, well, like me, I am doing depressed flow investigations. So we meet a lot of farmers, and they say, want to buy some food now. Every time, at least, they say 50% of agriculture food is wasted. So they want to, our university is cooperating with, this advisor is also my classmate too. So in our school, hydraulics divide into wastewater, diverse flows, reservoir investigation, and also green energy. So this is another big topic, and disaster only is one day per year, but nature uses every day. So I think green energy is also very important. So like Mr. Yang, he will present in JPGU next week, and he's going to talk about hydropower. Yeah. So hydropower is also needed, but in Taiwan we have, last week Fujihara sensei says also Japan has a drought problem. So this is not very reliable, but like him is 4 days, you have to use 4 days of waste, only 30 minutes. So you have to cook very fast, right? So electricity maybe is very important, especially in the mountain areas. We often have a lack of electricity. Yeah, so I think maybe we can learn better things around the world. Okay, that's all.
Maybe we can have about 5 minutes break.
Okay.
So come here at 3 o'clock.
3 o'clock, okay.
That's a bit.
欢迎大家来宇之川的实验室，可以走很多路哦，非常非常推荐。我大腿有点酸哎，现在才酸。我前几天都不会。 拍了我很想睡觉的样子。这个感觉就很像逢甲水工实验室的放大版，然后是海浪。
天井が50メートルで幅が4メートルになってます。
50米，宽度是4米。
很大。
赤いレールに防波板がついてます。
这个红色的建筑物就是造波器。
今は、規則波、レギュラーウェーブですね。規則波で、波を起こしてまして、
然后这就是浪波造成的浪波上升之境。
それで横から見ると分かるんですけれども、水深が少しずつ浅くなっていくようにしています。
好处是可以从侧面直接去测量它的水深。
波に来ると、波が壊れます。
然后根据水深的变化，然后海波进行变化。
波が、崩れています。崩れて最後再波ブレーキングウェーブがキャビを刻む。
随着水深慢慢下降，然后波形会慢慢被破坏掉。
で、こういう実験ですね。で、規則波の実験では主に、どっちかというと、防災面というより、規則波の研究では環境の研究をすることが多いです。
当然，这方面的研究除了防灾方向之外呢，还有其他方向都很有研究。
で、今から、津波を発生させます。
然后现在正在接下来我们先进行造波。
今は増波器を連続的に動かしてますけれども、津波の場合は、1回だけ大きく増波器を動かして、孤立波、アイソレーティドウェーブを発生させます。
然后现在进行接下来第二种波形，将向大家演示。
一旦この、規則波を止めまして、次に津波の準備をしますので、少しお待ちください。はい。
稍微等一下，马上波形就出现，新的一辆海浪就出现。
これからですね、はい、増波器を押して、はい、波が来ました。波が来ました。波が来ました。もう一回やりますね。はい。
第二遍。
その岸のところに置いていた構造物が津波によってかなり流されたことがわかると思います。もう一回やります。
上面有那个是机子自动的，第一个零售站到学生。
ありがとうございます。はい、じゃあ一応、はい、波のas a research group is place them on to the yeah, and as you see when tsunami rise up in the river, of course tsunami current passes through in the through along the roads, yeah, between the buildings.
台风冲刷到城市之后呢，会出现路面进行水会沿着路面进行冲刷。
ちなみに、2011年の東日本の大震災の時は津波が50メートルほど上流まで、50キロだった。50キロか。15キロじゃん。15 kilometer.
Really?
Yeah. Reaches
2011年这个地震，台湾向城市延伸了5公里的事情，全淹没。
これは多分 maybe I think it's a gas tank かな。ガスの
这个是
好像是塑胶哦。
中本さん、和歌山こういうのってガスタンクかなんかですよね、多分。
そうですね、多分。
火力発電所とか。
そうですね、はい。そういう模型だと。
和歌山には火力発電所とか、あと鉄工所とかたくさんの工場が沿岸部にあります。
在和歌山那边有非常多的这些发电厂，这些主机罐就是这些圆的。天然气
哦，气体
で津波が来ると非常にいろいろな災害が発生する。
在模型上面 in the model how do you fix this because a wave come it will break so how do you use glue or cement to make stable yeah how to
I don't know some
看起来很对
Screw it may be used.
可能是用
one and this four.
これだから2次元
这是2次元的话，那就是2的21次方。
哇，成大水工所是5个，对，海大的比较多一点。海洋 ，We have another university called National Ocean University. They have, I think it's 10, only 10.
Yes.
All can be 20% or much lower.
難しい。Okay, so please return to again. I'm sorry, sir.
简单的单字我有上课，
Because I have
我们
a
上课
lecture.
都有。
Sorry.
Thank you.
Thank you very much, everybody. Enjoy.
我要回去了。
我忘了开会了。
好想睡觉哟，好想睡觉。
因为时间来不及了啊。
要你问。
时间来不及而已，真的。
还是你叫他来带他老板给我。
是，这样是我没有买。对。这件赞，当然，这件也赞。瑞那件也好看。英语不好说，人也不好说，随便啦。
欢迎来到图水馆，不要让我看到这种
天啊，
东西。
靠腰。
又回到台湾。
欢迎来到水工实验室。
一样闷热。你戒指呢？找到了吗？
那在混凝土里面，那不是在沙里面。对啊。
さあ、ちょっと向こうにあっちの水路に水汲みに行きます。にあっちの水路も見せれるし。
はいはい、あ、なるほどなるほど。
So we have to take the water from there here.
But manual.
This is a manual experience. We need manpower.
Don't worry, we have race.
He only have one hand.
No, we have to take the bucket manually, I think.
Oh, why?
Because it's not connected to the system. Yeah, this is the first laboratory, I guess. The last laboratory we visited, the water system, right? I think they don't connect all the Guys, boys, we need your power.
We need the power.
对手受伤了。好。
Let's go.
我要去装水。
In the pond? その蛇口からは出ないんですか？
これね、ここの水入れて、こっちから。
上面有一个会日文的针筒。
So the water flow from here and you put the bucket here.
なんて無駄な。
超大两桶。干啥想到之前拱破啊，明天。
拱破。
那个啊，烧杯啊。
那个。
move。
怎么变你来了？
刚刚贤哥拿给我的。
哦。Because we need power.
你都想吃哦？
没有。哦靠！
我们实验室应该是需要整理。
我们要扩建吧？
我们要扩建，需要扩建。一楼是谁在管的啊？
一楼？
对啊，叶昭宪哦。我没有进去过啊，只有进去过2、3次吧。然后3次有2次是找朱丽玲他们聊天。
他现在对。
对啊，就看到朱丽玲，然后我就跑进去聊天。然后有一次是叶昭宪上课，然后我们过去。
我没有印象，做10分钟没进去过。
有，你有进去过。
如果是在旁边，这边就会多一点。
是模拟土石流，然后这边今天要用12度和18度，感眼睛好痒。
进沙了吗？我要把眼睛抠出来。跟主哥合照。
因为这还在录影中，好痒哦。
你现在在录吗？
对啊。
哦，那我刚说把你眼睛画出来，有录进去。
有啊有啊。大丈夫。No。
他にあるけど、一回貸してみて。あ、大丈夫っぽい。あ、いけたいけた。This is the pump. So water comes in here and then coming here, they go up.
Oh.
And
It's like underground
yeah, kind of
precipitation.
underground, yes. The underground and coming up.
还是请教授帮我们叫。
快下雨了，感觉快下雨了，超黑的。现在在等他们装水，然后做土石流实验。我刚才头盔。
最初すみません。プリパレーションがちょっと足りないね。またこれで、now we can use experiment. So maybe divide into the envelope and half here, half here. Now we have set to the 5 degrees. So you use segment up to the area. Yeah, this is. これを回してもらう。
俺がやったらダメだ。这设计真的，我要回去改一下我的，要改一下我的。好，这样，他的超级真的。
我们这比较符合实际状况。很漂亮。
流すときとか、こっちはそのスイッチを。それで。もう OK なら。
水石流跟层流跟土石流的差异，它这个大概只有一般的那个水流冲刷而已。 So why did you add this to form the roughness?
Roughness, yes. Because if we have no this kind of stick, it will be too smooth for the mountainous area. So sometimes we put some sand on, but sometimes we put this kind of sticks on.
Yes. So what kind of N value are you going to represent? Like this, the roughness, maybe 0.3.
Usually in a mountainous area, 0.03 to 0.5.
0.35. Okay.
So is it okay to start? You can do it on that part. So again, water is coming in. And erosion happening. And now, the difference, that's a difference. Wow. It's a segment for the sediment. It's very quick and more high concentration. But in the upper layer, I think you can see the water flow. So it's not very fast, so maybe once again you can see it. So it's quite a bit good.
You guys want to try?
No, maybe you do once again.
So, more angle?
You want more angle? Or I thought it was a little very fast, so maybe you can see once more. So, seeing in this tunnel, maybe 10 degrees, not so steep, but in the real case, it's a very steep area. But in the mountainous area, residential area, sometimes we have a very steep slope road or maybe channel. In that case, 10 degree often happens in Japan. I think in Taiwan too.
Come to Indonesia, 45 degree slope. We have everywhere.
Look accurate.
Thank you.
So maybe this will happen and coming to the residential area and this short road or channel, this kind of things can happen. So a very high velocity and comparing to the bed road, it's very high configuration. So it can be very. Okay. So now we can go to the 18 degrees. Here we go.
18. Go.
Just 18.
Not 18.
Not 18. That's too much. 啊，大丈夫。
把它弄尖尖的。
它会跳，会跳，
快把那个箱子推走。
So 18 degrees is very steep, but still, just sediment, it doesn't move. Then what happens, become sediment and water.
18。交给你。那种打开了，有一个那个按钮。
お願いします。
哦，滑路，开。哎，他帮你开了吗？对，他帮我开了。
因为它会跳。
对啊。
Very quick and high concentration.
这人应该就没了。
In the real scale, the rainfall can be up to 40.
一样18度
18，
哦。超级陡。这也是18嘛？对。好。
它就会控制。所以水保胶的那个平衡坡度会原来的2/3倍。So you can check 就懂啊。
来不及了，再一次吧，这样不准。
So you can check the degree. 对不对？
对啊。
好，所以是原来的2/3倍。
あと一回流して、 これで一回10日やろうか。これが10日を見せちゃうっていう。Open type Yeah. So this type.
Oh, grid one.
So this open type only fine sediment which is not doesn't come.
Yeah, fine sediment.
Only fine sediment this type doesn't come. See how the large mirror is. So after that, the sediment will be found.
但是它还是会有一半的碎石下来。
次についでに流木もこれに。
对啊，这还是危险。
忘れてました。
Next time, see also the UV level how much.
要关键在哪里？可以先把
Now here is a little space. Usually it's okay, so it's more effective. But this open type is good for the large border and the woody damage as well.
Too large, so the students say every time they have to put the sediment back again and again. This small one is good.
Yeah. Last one you see.
我的实验室啊，我们都在玩土沙的。啊，他们那个三楼，他们是玩水，那个
水药的那台吗？这里土沙跟你土沙
for the sediment, but for the woody damage it is not enough. So now in Japan we are trying to make the open type sabodama for the common. But in case in like a very volcanic area, like only 5 sediment no vegetation, in that case still close type sabodama is needed. So we have to choose which is the better one. sediment and liquid everything is stopped.
立掉了。
对啊，这个是缩小版的。那如果大的，
从这样子变成这样，我们
在河流上面用的是
古坑那边就有那个这个。
有实际的，就是有实际的这个。
我们上课有带学生去看过啊。
啊，所以它这个是用什么？ 没有啊，
用什么做？我的学生有。
竹子还是用木头？
没有啊，是用钢啊。
用钢啊。
这用竹子呢还得了？
对啊，我想说，不是因为它这个。
就换掉了。
好，石头对。
They have 12 meter. 12. This is too low.
这台不错。
But if too many people, it's
这个
too short.
可以买一台，考虑一下。